Long before the dinosaurs walked the earth, before mammals scurried in the shadows, before birds took flight, before flowers bloomed or grasses waved in the wind, before anything you would recognize as familiar life, the world was different, unimaginably different. 300 million years ago, all the continents you know today were fused into a single, massive landmass. Geologists call it Pangaea. For 160 million years, it dominated the planet. And during that incomprehensible span of time, life thrived on its surface. Now consider this. What if something intelligent evolved during those 160 million years? What if a civilization rose, built, thrived, and then vanished so completely that we will never find a single trace of it? This is not a story about ancient astronauts or pseudoscientific fantasies. This is a question posed by serious scientists, published in peer-reviewed journals, debated by NASA researchers. The question is simple. If an advanced civilization existed on Earth millions of years before humans, could we detect it in the geological record? And the answer, disturbingly, is this: probably not. You've heard of lost civilizations before. Atlantis, swallowed by the sea. Lemuria, a mythical land that never existed. Ancient cultures buried under sand or jungle. These are stories measured in thousands of years, perhaps tens of thousands. The ruins are there, if you look. Pottery shards, stone foundations, temples reclaimed by forests. We find them because they're recent. Recent enough that the evidence hasn't been destroyed. 300 million years is not recent. 300 million years is a span of time so vast that your mind cannot truly grasp it. The entire history of anatomically modern humans, every empire, every war, every discovery, every person who has ever lived, spans roughly 300,000 years. That's 1,000th of the time we're discussing. If you compressed Earth's history into a single 24-hour day, humans would appear in the final second before midnight. The civilization we're imagining would have existed before 10 p.m. And here's the problem. Earth doesn't preserve its history that well. The planet is a dynamic system. The crust moves. Oceans open and close. Mountains rise and erode. Sea floor gets pulled into the mantle and melted. After 300 million years, the surface of the planet has been recycled, buried, crushed, and rewritten so thoroughly that even massive stone monuments would be dust. Metal corrodes, wood rots. Bone fossilizes only under perfect conditions, and even then, it's rare. Technology? Forget it. Even our cities, our concrete and steel, would be obliterated in a fraction of that time. So if they existed, whoever they were, whatever they were, we would not find their cities, we would not find their tools, we would not find their bones in museums, reconstructed and labeled. They would be gone, utterly, completely, erased by the relentless machinery of geological time. The question you should be asking now is not whether they existed. The question is, how would we even know if they did? That's where the science gets interesting. In 2018, two researchers, an astrophysicist named Adam Frank and a climate scientist named Gavin Schmidt, the director of NASA's Goddard Institute for Space Studies, published a paper with a provocative title. They called it the Silurian Hypothesis, named after an episode of the British science fiction show Doctor Who, which featured intelligent reptiles living on Earth millions of years before humans. The paper asked a deceptively simple question: would it be possible to detect an industrial civilization in the geological record? Their conclusion was sobering. After about 4 million years, direct evidence, the kind of artifacts archaeologists rely on, would be nearly impossible to find. And we're not talking about 4 million years. We're talking about 250 million years at minimum, 60 times longer. In that span, even the indirect evidence, chemical signatures, isotope anomalies, traces of synthetic materials, would be faint, ambiguous, easily confused with natural processes. Frank and Schmidt weren't arguing that such a civilization existed. They were careful to emphasize that point. They were asking what the evidence would look like if it did. And in doing so, they forced us to confront an uncomfortable truth. Our methods for detecting ancient life are optimized for the recent past. We're good at finding things from thousands or even millions of years ago. We're terrible at finding things from hundreds of millions of years ago. The tools, the techniques, the very assumptions we use are built for a much shorter timescale. Which brings us back to Pangaea. If you wanted to hide a civilization so thoroughly that no future species would ever find it, you couldn't design a better scenario. Take a supercontinent, populate it with life for 160 million years, then break it apart. Let the pieces drift across the globe. Let plate tectonics pull some of those pieces into the mantle, where they melt and recycle. Let erosion wear down the mountains. Let volcanic eruptions bury the lowlands. And just to be sure, throw in the worst mass extinction event in Earth's history, an apocalypse so complete that 96% of all species died, to wipe the slate clean. That's what happened to Pangaea. And if any civilization existed on its surface, that's what happened to them. Now, you might be thinking, this is impossible. Intelligence is rare. It took billions of years of evolution to produce humans. The odds of it happening twice on the same planet are astronomically small. Perhaps. Perhaps intelligence is a singular fluke, a cosmic accident that occurred once in Earth's 4.5 billion year history. Or perhaps it's more common than we think. Perhaps it evolves, thrives for a time, and then gets erased by the next catastrophe. Perhaps the universe is full of civilizations that rose and fell, leaving no trace. Perhaps we're not the first. Perhaps we're just the latest. The thought is both humbling and terrifying. Humbling because it strips away our sense of uniqueness, our assumption that we are special, chosen, the culmination of history. Terrifying because it suggests that civilizations are ephemeral, fragile, erasable. If they existed and left no trace, what does that say about our own legacy? In 300 million years, will anyone know we were here? This is not a story with a clear answer. It's a thought experiment. A question posed to challenge our assumptions and stretch our understanding of deep time. The evidence, as you'll see, points in multiple directions. Some of it suggests the question is absurd. Some of it suggests we haven't looked carefully enough. And some of it suggests that the absence of evidence might itself be the most important clue. But before we can evaluate the evidence, before we can decide what's plausible and what's fantasy, we need to understand what we're looking for. We need to understand how Earth destroys its own history. We need to understand what traces, if any, a long-dead civilization might leave behind. And we need to understand the methods scientists are developing to search for those traces, not just on Earth, but on distant worlds orbiting distant stars. Because if we're asking whether an ancient civilization existed on Pangaea, we're also asking a deeper question: are we alone? Have we ever been alone? And if intelligence has arisen before, if it's been erased before, what does that mean for our future? The journey begins not with Pangaea, but with the tools we'll use to search for its ghosts. We need to understand the science of detection before we can understand what might have been lost. So let's start there. Let's start with the question that Adam Frank and Gavin Schmidt asked in 2018. Let's start with the Silurian Hypothesis. The paper appeared in April 2018 in the International Journal of Astrobiology. Its title was straightforward: The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The authors were Adam Frank, an astrophysicist at the University of Rochester, and Gavin Schmidt, director of NASA's Goddard Institute for Space Studies. These were not fringe researchers chasing pseudoscience. These were serious scientists asking a serious question. The name itself came from science fiction. In the British television series Doctor Who, an alien species called the Silurians, intelligent reptilian humanoids, lived on Earth millions of years before humans evolved. When the Doctor encounters them, they claim to be Earth's original civilization, forced into hiding by a planetary catastrophe. Frank and Schmidt borrowed the name as a nod to the concept, a way of making an abstract question tangible. Could something like the fictional Silurians have actually existed? Their motivation wasn't to prove that ancient civilizations existed. Frank has said explicitly that he doubts any previous industrial civilization arose on Earth. The motivation was different, more subtle. They wanted to know what traces our own civilization would leave behind if it vanished today and someone searched for evidence millions of years later. And in asking that question about us, they stumbled onto a deeper puzzle. How would we recognize such traces from the deep past? The answer is unsettling. After about 4 million years, almost all direct evidence, the kind of physical artifacts archaeologists depend on, would be gone or unrecognizable. And 4 million years is nothing compared to the timescales we're discussing. Pangaea existed more than 250 million years ago, 60 times longer. So if you can't find cities or tools or bones, what can you find? You look for chemical fingerprints, anomalies in the geological record, traces so subtle that you'd miss them unless you knew what to look for and where to look. Frank and Schmidt identified several markers that an industrial civilization might leave behind, signatures that could persist for tens or even hundreds of millions of years if you knew how to read the rocks. The first is carbon, specifically the ratio of carbon isotopes in sedimentary layers. When you burn fossil fuels, coal, oil, natural gas, you release carbon that's been locked underground for millions of years. This ancient carbon is isotopically light, meaning it's depleted in the heavier carbon-13 isotope relative to carbon-12. When that carbon enters the atmosphere and oceans, it changes the ratio. It leaves a signature. Scientists call this the Suez effect, named after the Austrian chemist who first identified it in the 1950s. The Anthropocene, the current geological epoch defined by human activity, is already marked by this carbon anomaly. Future geologists studying rocks from the 21st century would see a sharp spike in light carbon corresponding to the Industrial Revolution. It's there in ice cores, ocean sediments and tree rings, clear as day. The question is, would it still be there in 250 million years? Maybe. Sediment layers preserve chemical signatures for immense stretches of time. The problem is that other processes can produce similar signals. Volcanic eruptions release carbon from the mantle. Massive forest fires dump carbon into the atmosphere. Methane clathrates, frozen methane on the ocean floor, can destabilize and release enormous quantities of greenhouse gases, creating a spike that looks industrial. Natural events can mimic the fingerprints of civilization. Which brings us to the second marker, synthetic isotopes. These are unambiguous. Plutonium-244 and iodine-129 are produced only by nuclear fission. They don't occur naturally on Earth in significant quantities. Plutonium-244 has a half-life of 80 million years. Iodine-129 has a half-life of 16 million years. If you found elevated levels of these isotopes in ancient rocks, you'd have a smoking gun. No natural process creates them. Their presence would be direct evidence of nuclear technology. The catch, of course, is that you'd have to find them. After 250 million years, even long-lived isotopes decay. Plutonium-244 would be reduced to a tiny fraction of its original concentration. You'd need extremely sensitive instruments, and you'd need to know exactly where to look. Sampling random rocks wouldn't work. You'd need targeted searches in specific sediment layers, in regions that might have hosted industrial activity. And how do you find those regions if you don't know where the cities were? The third marker involves fertilizers. Industrial agriculture uses synthetic nitrogen and phosphorus compounds. These leave geochemical signatures in soil and sediment. Elevated nitrogen-15 ratios. Phosphorus deposits in unexpected locations. The problem here is the same as with carbon. Natural processes can produce similar patterns. Nitrogen-fixing bacteria, upwelling ocean currents, volcanic ash, all can alter the chemical makeup of sediments in ways that mimic agriculture. Frank and Schmidt also considered plastic. Modern plastics are polymers, long chains of carbon-based molecules that don't exist in nature. When plastics break down, they leave behind chemical traces, detectable hydrocarbon patterns. These could persist for millions of years in sediment. The difficulty is that heat and pressure eventually break down even synthetic polymers. Subduction, metamorphism, and erosion all degrade the signal. After 250 million years, plastic residues would be fragmentary at best, easily mistaken for natural organic compounds. Temperature is another clue. Rapid global warming can indicate industrial activity, especially if it's coupled with carbon isotope anomalies. The current Anthropocene warming is happening faster than almost any natural climate shift in the geological record. If a similar spike occurred in the Permian, it might raise questions. The challenge is distinguishing industrial warming from volcanic warming or methane release warming. All three produce similar signals. You'd need additional evidence to make the case. So where does this leave us? Frank and Schmidt concluded that detecting an ancient industrial civilization is technically possible, but only under ideal conditions. You'd need multiple lines of evidence converging in the same location and time period. A carbon spike, a temperature spike, synthetic isotopes, and chemical anomalies all appearing together. Even then, you'd face skepticism. Critics would argue for natural explanations, volcanism, impacts, methane clathrates, ocean anoxia. The other problem is that we're not looking. The geological community isn't systematically searching Permian or Carboniferous rocks for technosignatures. Why would they? The assumption is that no previous civilization existed, so there's no reason to check. It's a bit circular. We don't find evidence because we're not looking. We're not looking because we don't expect to find anything. And we don't expect to find anything because we haven't found anything. Frank and Schmidt's paper was, in many ways, a call to action. They weren't claiming ancient civilizations existed. They were pointing out that we lack the tools and methods to rule them out definitively. If someone asked, could you prove that no industrial civilization existed on Earth 250 million years ago? The honest answer would be, no, we couldn't. Not with current techniques, not with current data. This might seem like an academic exercise, a thought experiment with no real-world application. Frank and Schmidt disagree. Their work has implications for astrobiology, the search for life on other planets. If we can barely detect our own potential predecessors on Earth, a planet we've studied intensively for centuries, how will we detect alien civilizations on exoplanets orbiting distant stars? What technosignatures should we look for in the atmospheres of those worlds? What chemical anomalies would indicate industrial activity? The Silurian hypothesis forces us to refine our methods. It challenges us to think more carefully about what traces civilizations leave and how long those traces endure. And it reminds us that absence of evidence is not evidence of absence. Just because we haven't found something doesn't mean it wasn't there. Which brings us back to Pangaea. If a civilization existed on that supercontinent, the Silurian hypothesis tells us what we'd be looking for. Subtle chemical signatures, buried in rock layers that have survived 250 million years of geological upheaval, carbon anomalies, isotope spikes, temperature fluctuations. No one has found those signatures. Not yet. The question is whether they were ever there to begin with, or whether Earth's relentless recycling has already erased them. To understand why evidence might be gone, we need to understand the forces that destroy it. We need to understand how the planet erases its own past. We need to understand plate tectonics. Earth is not a static museum. It's an active, churning system that constantly rewrites its own surface. The ground beneath your feet is moving, imperceptibly slow but relentless. Continents drift, oceans open and close, mountains rise and fall, and in the process, the planet destroys almost everything that came before. This is plate tectonics, the geological theory that explains how Earth's outer shell is broken into massive slabs, plates that slide over the semi-molten mantle below. These plates diverge, collide, and scrape past one another at speeds measured in centimeters per year, slow by human standards, catastrophic over geological time. At mid-ocean ridges, new crust is born. Magma wells up from the mantle, cools and solidifies into fresh seafloor. This process, called seafloor spreading, pushes the plates apart. The Atlantic Ocean, for example, is widening by about 2.5 centimeters each year. That's roughly the speed your fingernails grow. Over millions of years, that tiny increment adds up. The Atlantic has opened more than 5,000 kilometers since the breakup of Pangaea began 200 million years ago. New crust forming means old crust must go somewhere. The planet's surface area doesn't change, so the system balances itself through destruction. At subduction zones, deep ocean trenches where plates converge, old oceanic crust is pulled down into the mantle. It descends, heats up, and melts. The rock that once formed the seafloor gets recycled into magma, which eventually erupts through volcanoes to form new crust elsewhere. The cycle repeats endlessly. This recycling is efficient. Almost no oceanic crust older than 200 million years exists anywhere on Earth. The oldest patches, found in the Mediterranean and the Western Pacific, date to the early Jurassic period. Everything older has been subducted, consumed by the mantle, erased. If you're looking for evidence of something that happened 250 million years ago, you won't find it on the ocean floor. The ocean floor from that time no longer exists. Continental crust fares better, but only slightly. Continents are thicker and more buoyant than oceanic crust, so they resist subduction. They collide, buckle, and pile up into mountain ranges instead of sinking into the mantle. The Himalayas, the Alps, the Rockies, all are products of continental collisions. These mountains preserve older rocks, some billions of years old, uplifted from deep within the crust. Yet even continental surfaces are young in the places that matter most. The exposed surface, the part you can walk on, dig into, sample for fossils, is constantly being reworked by erosion, sedimentation, and tectonic activity. Rivers carve valleys, glaciers grind down peaks, wind strips away soil, sediment buries old surfaces under new layers. The result is that while ancient rocks exist, ancient surfaces do not. The landscape you see today is not the landscape of the Permian. It's not even close. Consider the Appalachian Mountains, which run along the eastern United States. These mountains formed during the assembly of Pangaea, roughly 300 million years ago, when the continent of Laurentia collided with Gondwana. At their peak, they may have rivaled the Himalayas, towering ranges with summits scraping the sky. Today, they're worn nubs, gentle slopes covered in forest. 250 million years of rain, ice, and wind have ground them down. The rock is still there, but the original surface is gone, eroded and washed into the sea. If you built a city on Pangaea, on the flanks of those mountains, what would remain today? Nothing. The stone foundations would have weathered into sand. The sand would have washed downstream and been deposited in deltas or ocean basins. Some of those basins would have been subducted. Others would have been buried under kilometers of newer sediment. Either way, your city is gone. Not hidden, not waiting to be discovered. Gone. The same logic applies to artifacts. Wood rots within centuries, even under ideal conditions. Metal corrodes. Iron rusts away in thousands of years. Bronze lasts longer, but even bronze degrades when exposed to water and air. Bury it deep enough in an anoxic environment, and it might survive longer. But after 250 million years, even deeply buried metal would be crushed, altered, or destroyed by the heat and pressure of geological processes. Plastics, ironically, are among the more durable materials. Modern polymers resist biological decay, and some could persist for millions of years in sediment. The problem is that they degrade chemically. Heat breaks polymer chains. Pressure compacts them. Microbes, given enough time, learn to digest them. After tens of millions of years, even plastic would be reduced to unrecognizable hydrocarbon residues, easily mistaken for natural organic matter. Concrete crumbles, glass shatters and weathers into sand, stone monuments erode. The Great Pyramid of Giza, one of the most durable structures humans have ever built, will not survive another 250 million years. Erosion will reduce it to rubble. The rubble will be buried or scattered. The landscape itself will change so much that no one would recognize the location. And this is just the fate of structures. What about fossils? Surely bones at least could survive. They could, under the right conditions. Fossilization requires rapid burial in sediment, usually in water, where oxygen levels are low and decay is slow. The organic material in the bone is gradually replaced by minerals, turning the bone into stone. This process preserves the shape but not the original material. Over millions of years, fossilized bones can survive tectonic compression, heating, and burial under new layers of rock. The catch is that fossilization is rare. Most organisms that die are consumed by scavengers, decomposed by bacteria, or scattered by the elements. Only a tiny fraction, estimates suggest less than 1/10%, ever become fossils, and of those fossils, only a fraction are ever found. Most remain buried in rocks we never access. Some are destroyed by erosion before anyone discovers them. Others are in rocks that have been subducted or metamorphosed beyond recognition. Consider the dinosaurs. They dominated Earth for 165 million years. Thousands of species across every continent, in nearly every environment. Yet we've identified only about 1,000 species from fossils. The fossil record captures a minuscule sliver of dinosaur diversity. The vast majority left no trace. If dinosaurs, with their massive bones and global distribution, are so poorly represented, what chance does a soft-bodied organism have? Or a tool-using species whose population was small and whose technology was biodegradable? The answer is almost none. If an intelligent species existed on Pangaea, and if they used stone tools, those tools would be nearly indistinguishable from naturally fractured rocks after 250 million years. If they built with wood or bone, no trace would remain. If they worked metal, the metal would have corroded away. If they carved symbols into stone, the stone would have eroded smooth. The only hope for detection lies in chemistry. Geochemical anomalies, as Frank and Schmidt outlined, might survive in sediment layers that have avoided subduction and metamorphism. Carbon isotope spikes, synthetic isotopes, phosphorus deposits. These signatures could persist, faint and ambiguous in the right rocks. Finding them would require systematic searches in precisely the right locations, locations that correspond to regions where industrial activity might have occurred. The problem is that we don't know where those locations would be. Pangea's coastline is now scattered across multiple continents. The interior basins have been uplifted, eroded, or buried. The seafloor from that time is gone, subducted into the mantle. We'd be searching for needles in a haystack the size of a planet, looking for signals we can barely define, in rocks that have been cooked, crushed, and rearranged for 250 million years. Plate tectonics is the first great eraser. It recycles the crust, buries the old surface, and destroys nearly all physical evidence of the past. Erosion is the second. Rain, wind, ice and rivers grind away mountains and fill valleys with sediment, obliterating landscapes. And then there's the third eraser, the one that makes all the others seem gentle by comparison. The third eraser is extinction, specifically the Permian Triassic extinction, the worst mass die-off in Earth's history. If any civilization existed on Pangaea, this event would have been their apocalypse. 252 million years ago, the world nearly ended, not metaphorically, not in the sense of a difficult period or a regional catastrophe. The world, life on Earth in all its forms, came within a razor's edge of total annihilation. What followed was the single worst mass extinction event in the planet's history, an apocalypse so complete that scientists struggle for words to describe it. They settled on a simple phrase, the Great Dying. The numbers are staggering. In the oceans, roughly 96% of all marine species vanished. Some researchers, after accounting for background extinction rates, have revised this figure downward to 81%. Either way, the oceans were nearly sterilized. Reefs collapsed. The seafloor became a graveyard. Trilobites, which had thrived for nearly 300 million years, disappeared forever. Rugose and tabulate corals, which had built vast underwater structures, went extinct. Blastoids and crinoids, two major groups of echinoderms, were wiped out. Entire classes of life simply ceased to exist. On land, the devastation was nearly as severe. Roughly 70% of terrestrial vertebrate species died. Large herbivores were hit hardest. Carnivores, deprived of prey, followed. Amphibians, already in decline, suffered catastrophic losses. Even insects, normally resilient to extinction events, experienced the worst die-off in their history. This is the only known mass extinction to significantly impact insects, a testament to how severe the conditions must have been. Plants died on a massive scale. Forests that had covered Pangaea for millions of years withered and collapsed. In the fossil record, this is marked by a sudden absence of coal deposits. Coal forms from plant matter that accumulates in swamps and peat bogs. For millions of years after the extinction, no coal formed anywhere on Earth. Scientists call this the coal gap, a period when plant life was so sparse that insufficient biomass accumulated to create coal seams. The gap lasted roughly 10 million years. What replaced the forests? Fungi. In rock layers corresponding to the extinction boundary, paleontologists find an explosive proliferation of fungal spores, far more than would normally appear. This fungal spike suggests that fungi were feasting on an abundance of dead and decaying organic matter. The world had become a rotting wasteland, blanketed in the remains of trees and plants that had died en masse. The extinction didn't happen overnight, though by geological standards it was astonishingly fast. Current estimates suggest the worst of the dying occurred over a span of 60,000 to 100,000 years. Some researchers argue it was even quicker, perhaps as little as 20,000 years in certain regions. On a human timescale, this seems like an eternity. On a geological timescale, it's the blink of an eye. For comparison, the extinction that killed the dinosaurs 66 million years ago, the the one caused by the Chicxulub asteroid, unfolded over a similarly brief period. What caused the Great Dying? The answer, frustratingly, is not entirely clear. Multiple factors likely combined, each amplifying the others in a cascade of environmental collapse. The primary suspect is volcanism, specifically the eruption of the Siberian Traps, one of the largest volcanic events in Earth's history. Around 252 million years ago, a colossal outpouring of lava began in what is now Siberia. The eruptions lasted for roughly 1 million years, though the peak activity may have been concentrated in a much shorter window. The amount of lava released was staggering. Estimates range from 1 to 4 million cubic kilometers, enough to cover an area roughly 2/3 the size of the continental United States. The lava itself was catastrophic for local ecosystems, but the real damage came from the gases. Volcanic eruptions release enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. Carbon dioxide, a greenhouse gas, caused rapid global warming. Temperatures rose by an estimated 3 to 5 degrees Celsius, perhaps more in some regions. Sulfur dioxide, on the other hand, initially caused cooling by reflecting sunlight, but it also mixed with water vapor to form sulfuric acid, which fell as acid rain. The combination, warming, acidification, and atmospheric pollution, created conditions hostile to most life. The warming had particularly dire consequences for the oceans. As water temperatures rise, the ocean's ability to hold dissolved oxygen decreases. Warmer water also increases the metabolic rates of marine animals, meaning they need more oxygen even as less becomes available. The result was widespread anoxia, dead zones where oxygen levels dropped so low that nothing could survive. Studies suggest that roughly 80% of the ocean's oxygen was lost during the extinction. About half of the seafloor became completely anoxic. Marine life suffocated. Ocean acidification compounded the problem. Carbon dioxide dissolves in seawater, forming carbonic acid. This lowers the pH, making it harder for organisms with calcium carbonate shells or skeletons, like corals, mollusks, and many plankton species, to build and maintain their structures. The fossil record shows that calcifying organisms were among the hardest hit during the Permian extinction. Some researchers have proposed an additional trigger, an asteroid impact. In the late 1990s, geologist Luan Becker discovered fullerenes, soccer ball-shaped carbon molecules, in rock layers corresponding to the extinction boundary. These fullerenes contained trapped helium and argon, with isotopic signatures suggesting an extraterrestrial origin. Becker argued that an asteroid strike could have delivered these molecules while also triggering massive environmental disruption. Other scientists found evidence of shocked quartz and high concentrations of light sulfur in boundary layers, both consistent with an impact. The asteroid hypothesis remains controversial. Unlike the Chicxulub impact, no definitive crater has been identified for the Permian extinction. Some researchers argue that the geochemical signatures Becker found could have alternative explanations. The consensus leans toward volcanism as the primary driver, with an asteroid as a possible contributing factor. Regardless of the exact mechanisms, the result was the same. The world became uninhabitable for most species. On land, temperatures soared, droughts intensified, acid rain fell, forests died. In the oceans, oxygen vanished, acidity spiked, and food webs collapsed. Life clung to survival in scattered refugia, pockets of habitability where conditions were slightly less catastrophic. Recovery was agonizingly slow. For millions of years after the extinction, ecosystems remained impoverished. The few species that survived faced a world of empty niches and limited competition. One of these survivors was Lystrosaurus, a small herbivorous synapsid about the size of a pig. Lystrosaurus was unremarkable before the extinction. one of many species in a diverse fauna. After the extinction, it became the most common land vertebrate on Earth, making up an estimated 95% of all terrestrial life in some regions. It was a disaster taxon, an opportunist that thrived in the ecological vacuum left by the catastrophe. Over time, other species recovered and diversified. New groups emerged. The Triassic period, which followed the Permian, saw the rise of the first dinosaurs and the evolution of early mammals from synodont ancestors. Life rebuilt itself, but it took more than 10 million years for ecosystems to regain even a fraction of their former complexity. Now consider what this means for a hypothetical civilization. If any intelligent species existed on Pangaea before the Permian-Triassic extinction, this event would have been their end. Not a slow decline, not a gradual fade-out, but an abrupt, catastrophic annihilation. Their cities would have been abandoned as the environment became unlivable. Their populations would have dwindled and died as food sources vanished and temperatures soared. Their knowledge, their culture, their technology, all would have perished with them. And even if a few individuals survived in isolated refugia, clinging to life for generations, they would have been reduced to a handful. They would have faced a world so hostile, so depleted, that rebuilding would have been impossible. They would have watched their civilization collapse, unable to stop it. The extinction would have erased them as thoroughly as plate tectonics erased their artifacts. No monuments, no records, no descendants to remember. Just a faint chemical signature buried in rock, indistinguishable from the natural chaos of the event itself. If they existed, they are gone. Not hidden in some undiscovered corner of the fossil record. Not waiting to be found by the right archaeologist in the right place. Gone. Erased. Forgotten. The Great Dying was the ultimate reset button. It cleared the world and allowed evolution to start again from a drastically reduced set of survivors. And it raises a question we'll return to later. If extinction events can erase entire branches of the tree of life, how many other experiments has evolution tried? How many times has intelligence arisen only to be snuffed out by catastrophe? For now, we've established the obstacles. We've seen how plate tectonics recycles the crust, how erosion wears away the surface, how extinction wipes the slate clean. We understand why finding evidence of a pre-Pangean civilization would be nearly impossible. Now, at last, we can turn to Pangaea itself. We can explore what that world was like, what life inhabited it, and whether anything on that ancient supercontinent could have given rise to intelligence. We can ask, what was Pangaea? 335 million years ago, the continents began to collide. The movement was imperceptible at any human timescale, just a few centimeters per year. But over millions of years, the fragments of Earth's crust converged. Laurentia, Gondwana, Baltica, Siberia, land masses that would one day become North America, South America, Africa, Europe, Asia, Australia, and Antarctica, drifted together like pieces of a puzzle assembling themselves. By roughly 299 million years ago, at the start of the Permian period, they had fused into a single, colossal supercontinent. Geologists call it Pangaea, from the ancient Greek words meaning all Earth. The name is fitting. Nearly every piece of continental crust on the planet was joined together in one unbroken landmass. If you stood on the shore of what is now Brazil and started walking north and east, you could travel through Africa, cross into Europe, continue through Asia, and eventually reach the Arctic regions without ever encountering an ocean. You could walk from the South Pole to the North Pole on dry land. No sea would stop you. The supercontinent was shaped like a thickened letter C, with the curve opening to the east. The interior of the sea was a vast ocean basin called the Tethys Sea, an embayment that cut deep into the eastern side of Pangaea. This was no minor inlet. The Tethys was thousands of kilometers across, warm and relatively shallow, teeming with marine life. It acted as a conduit, allowing tropical ocean currents from the superocean Panthalassa, the single world-spanning sea that surrounded Pangaea, to penetrate into the heart of the supercontinent's eastern edge. Panthalassa itself was immense beyond comprehension. It covered roughly 70% of Earth's surface. Modern oceans, the Atlantic, the Pacific, the Indian, are remnants or descendants of Panthalassa and the Tethys. The Pacific Ocean is the largest surviving fragment of Panthalassa's vastness. Everything else opened later, after Pangaea broke apart. The geography of Pangaea was as alien as its scale. Mountains dominated the interior, thrust upward by the collisions that had assembled the supercontinent. The central Pangean mountains, also called the Variscan or Hercynian ranges, stretched for thousands of kilometers across what is now eastern North America and western Europe. At their peak, these mountains may have rivaled the Himalayas in height and grandeur. They formed a massive barrier running roughly east-west, dividing the northern and southern halves of Pangaea and profoundly influencing the climate. Climate on Pangaea was extreme. The sheer size of the landmass created conditions unlike anything seen today. Continental interiors, far from any moderating ocean influence, experienced wild temperature swings, scorching heat during the day, bitter cold at night. Seasonal variations were severe. In the regions that would become modern-day Colorado, Oklahoma, and northern Texas, vast deserts stretched for hundreds of thousands of square kilometers. These were not the scenic, sandy deserts of the Sahara or the Mojave. They were harsher, more barren, with little vegetation and brutal temperature extremes. The interior deserts of Pangaea may have been among the most inhospitable places on Earth. Imagine standing in the center of the supercontinent, thousands of kilometers from the nearest coast. The air is dry, almost sterile. Dust devils whip across barren plains. During the day, temperatures soar above 50 degrees Celsius. At night, they plummet. There are no rivers here, no lakes, no reliable sources of water. Life, if it exists at all, clings to the margins, around ephemeral ponds that form after rare rainstorms, or in underground burrows where the temperature stays tolerable. The coasts, by contrast, were lush and humid. The edges of Pangaea, especially in equatorial regions, experienced intense monsoons. Warm, moist air from Panthalassa collided with the continental landmass, dumping torrential rains during the wet season. Forests grew thick and dense in these regions, fed by the seasonal floods. Rivers carved deep valleys, carrying sediment from the mountains to the sea. Deltas formed, sprawling wetlands where freshwater and saltwater mixed. The southern coast of Pangaea, encompassing what is now South America, Southern Africa, India, Australia, and Antarctica, was particularly verdant during the early and middle Permian. Forests of Glossopteris, a genus of seed ferns with distinctive tongue-shaped leaves, dominated these regions. Glossopteris thrived in the temperate to cool climates of the southern hemisphere, forming vast woodlands that stretched across Gondwana, the southern component of Pangaea. These forests were the foundation of ecosystems that supported herbivores, carnivores, and a rich diversity of invertebrates. The northern regions of Pangaea, meanwhile, were home to different plant communities. Conifers and ferns dominated the highlands and coastal lowlands. Seed plants, gymnosperms, had an advantage in the drier conditions that prevailed across much of the supercontinent's interior and mid-latitudes. Unlike ferns, which rely on water for reproduction, gymnosperms produce seeds that can survive in dry conditions. This adaptation allowed them to colonize regions that would have been inhospitable to earlier plant groups. Pangaea's climate was not static. Over the course of its existence, global temperatures fluctuated. The late Carboniferous and early Permian saw the tail end of an ice age, with glaciers covering parts of Gondwana. As the ice retreated, temperatures warmed. By the middle Permian, Earth was warmer than it is today, and the trend continued into the late Permian, culminating in the extreme heat that may have contributed to the Permian-Triassic extinction. The supercontinent existed for 160 million years. Let that number settle. 160 million years. For comparison, the entire genus Homo, the lineage that includes modern humans and our closest extinct relatives, has existed for roughly 3 million years. Recorded human history spans about 6,000 years. Anatomically, modern humans have been around for 300,000 years. Multiply that by more than 500, and you begin to approach the duration of Pangea's existence. During that immense span, life evolved, diversified, and adapted to the unique conditions the supercontinent imposed. New species arose, old ones went extinct. Entire ecosystems formed and collapsed. The Permian period alone, just the last third of Pangea's existence, lasted 47 million years, longer than the entire Cenozoic era, the age of mammals that followed the extinction of the dinosaurs. 160 million years is enough time for evolution to try countless experiments. It's enough time for intelligence to evolve if the conditions are right. It's enough time for civilizations to rise and fall, not once but potentially many times. And it's more than enough time for any trace of those civilizations to be erased by the forces we've already described: plate tectonics, erosion, and extinction. Pangaea began to fracture around 200 million years ago during the early Jurassic period. Rifts formed as mantle plumes pushed upward from below, stretching and weakening the crust. The supercontinent split into two major land masses, Laurasia in the north and Gondwana in the south. These, in turn, continued to break apart over the next 150 million years, drifting into the configuration we recognize today. When Pangaea broke, the evidence of its existence went with it. The coastlines where civilizations might have built cities are now scattered across multiple continents, separated by thousands of kilometers of ocean. The interior basins where rivers once flowed are now mountain ranges or buried under sediment. The mountains that dominated the landscape have been eroded down to their roots. The seafloor that bordered Pangea's coasts has been subducted into the mantle, recycled and lost. What remains is fragmentary. Fossil sites in South Africa, Russia, China, and North America preserve glimpses of Permian life, but these are snapshots, not a continuous record. Vast regions of Pangaea are represented by little or no fossil evidence. The northern interior, the equatorial belt, and much of the southern coastal zone are poorly sampled. We know life existed there. The climate models and the fragmentary fossils we do have make that clear, but the details are lost. This is the stage on which our hypothetical civilization would have existed. A supercontinent larger than any landmass today, dominated by mountains and deserts in its interior, fringed by lush forests and monsoon-fed coastlines. A world that lasted 160 million years, an expanse of time so vast that human minds struggle to grasp it. If intelligence arose during that span, where would it have emerged? Almost certainly not in the harsh interior deserts. Life there was sparse, conditions brutal. The coasts are the logical candidates, regions with abundant resources, moderate climates, access to both land and sea. River valleys, deltas, coastal plains, places where food was plentiful and water reliable. And if they built something, cities, monuments, infrastructure, where would the evidence be now? Scattered across continents, buried under kilometers of sediment, subducted into the mantle or eroded into dust. The coastlines of Pangaea are not the coastlines of today. The rivers have changed course or vanished. The mountains have worn down. The land itself has been reshaped beyond recognition. This is Pangaea. This is the world we're searching for signs of a lost civilization. And now that we've seen the stage, we can ask, what walked across it? What lived on this supercontinent? What creatures dominated the land, the seas, the skies? And could any of them have given rise to intelligence? The rulers of Pangaea were not dinosaurs. Dinosaurs would not appear for another 30 million years, long after the supercontinent had begun to fracture. The dominant land animals during Pangaea's existence belonged to a different lineage entirely, one that most people have never heard of. They were called synapsids, and they were, in a very real sense, our ancestors. Synapsids are often described as mammal-like reptiles, though this phrase is misleading. They were not reptiles that happened to resemble mammals. They were a separate branch of the evolutionary tree, a lineage that split from the reptilian line more than 300 million years ago. Some synapsids retained reptilian features, sprawling limbs, scaly skin, while others evolved traits we associate with mammals: upright posture, differentiated teeth, and possibly fur. By the late Permian, the most advanced synapsids were closer to mammals than to reptiles. They were the stock from which all mammals, including humans, would eventually descend. For over 100 million years, synapsids dominated terrestrial ecosystems. They were the apex predators. They were the largest herbivores. They occupied nearly every ecological niche on land. If you walked across Pangaea during the Permian period, the animals you encountered, whether basking on rocks, stalking through forests, or grazing in open plains, would almost all have been synapsids. The earliest synapsids, known as pelycosaurs, appeared in the late Carboniferous period, around 320 million years ago. One of the most recognizable was Dimetrodon, a predator roughly the size of a large dog, distinguished by the enormous sail-like structure on its back. The sail was supported by elongated spines extending from the vertebrae and covered in skin. Its function remains debated. Some paleontologists believe it served as a thermoregulatory device, helping Dimetrodon warm up quickly by catching sunlight or cool down by dissipating heat. Others suggest it played a role in display, a visual signal used to intimidate rivals or attract mates. Dimetrodon is frequently mistaken for a dinosaur, lumped together with Tyrannosaurus rex and Velociraptor in children's books and museum gift shops. This is incorrect. Dimetrodon lived and went extinct long before the first dinosaurs evolved. It was a synapsid, more closely related to you than to any dinosaur. Its skull structure, jaw mechanics, and teeth align it firmly with the mammalian lineage. Pelycosaurs like Dimetrodon were primitive by later standards. Their limbs sprawled outward from their bodies in a reptilian stance, limiting their agility and endurance. They were likely ectothermic, cold-blooded, relying on external heat sources to regulate body temperature. By the Middle Permian, around 270 million years ago, pelycosaurs had largely disappeared, replaced by a more advanced group, the therapsids. Therapsids were a major evolutionary leap. Their limbs moved inward, positioned more directly beneath the body, giving them a more upright, efficient gait. This change improved their locomotion, allowing them to move faster and with greater stamina. Their skulls became more robust, with stronger jaws and more complex teeth. Unlike pelycosaurs, which had relatively uniform teeth, therapsids developed differentiated dentition, incisors for cutting, canines for gripping, and molars for grinding. This specialization allowed them to process food more efficiently, extracting more energy from their diet. One group of therapsids, the Gorgonopsians, became the apex predators of the late Permian. These were fearsome carnivores, some as large as modern lions, with elongated saber-like canines that could reach 10 centimeters in length. Gorgonopsians had powerful jaws and muscular bodies built for ambush hunting. Fossil evidence suggests they preyed on the large herbivores of the time, using their canines to deliver killing bites. They were the dominant land predators for millions of years until the Permian Triassic extinction wiped them out. Another major group was the dicynodonts, herbivores characterized by their beaked mouths and, in many species, a pair of tusks protruding from the upper jaw. The name dicynodont means two dog teeth, a reference to these tusks. Dicynodonts ranged in size from small, rat-sized creatures to massive animals weighing over a ton. They were incredibly diverse and successful, occupying herbivorous niches across Pangaea. Some, like Lystrosaurus, were squat and burrowing, built low to the ground with powerful forelimbs for digging. Others were larger and more robust, resembling hippos or pigs. Evidence suggests that many dicynodonts were endothermic, warm-blooded. Bone histology studies show growth patterns consistent with high metabolic rates. Some fossil sites have even preserved indirect evidence of fur found in the fossilized dung of Gorgonopsians. If dicynodonts had fur, it implies they maintained their body temperature internally, a key characteristic of endothermy. Warm-bloodedness would have given them a significant advantage in Pangea's variable climates, allowing them to remain active during cooler periods when cold-blooded animals would be sluggish. The most advanced therapsids were the cynodonts, a group that emerged in the late Permian and flourished in the Triassic. Cynodonts were small to medium-sized, generally no larger than a modern dog, though a few species grew larger. What made them remarkable was not their size, but their anatomy. Cynodonts possessed features that are unmistakably mammalian. Their skulls show evidence of a secondary palate, a bony structure that separates the nasal passages from the mouth, allowing them to breathe while eating. This is a hallmark of mammals. Their teeth were highly differentiated, with clear distinctions between incisors, canines, premolars, and molars. Their jaws were powerful and precise, capable of complex chewing motions. Some cynodonts show pits and grooves on their snouts, features associated with whiskers in modern mammals. Whiskers are sensory organs, requiring a sophisticated nervous system to process the information they provide. If cynodonts had whiskers, they had the neural infrastructure to support them. Cynodonts were likely warm-blooded. Their bone structure, small size, and active lifestyle all point toward high metabolic rates. Some species may have had fur, though direct fossil evidence is lacking. Their brains, relative to body size, were larger than those of earlier synapsids, though still smaller than those of modern mammals. They were intelligent, adaptable, and highly successful. Cynodonts survived the Permian Triassic extinction and went on to dominate the early Triassic. From this group, true mammals would eventually evolve. The ecosystems of Pangaea, dominated by these synapsids, were complex and dynamic. Herbivorous dicynodonts grazed on the ferns and seed plants that covered the lowlands. They were hunted by Gorgonopsians, which lurked in the undergrowth, waiting to ambush prey. Smaller carnivorous therapsids preyed on insects, small vertebrates, and each other. Scavengers picked over carcasses. Burrowing species created underground refuges, escaping the harsh surface conditions. Social behaviors emerged. Some dicynodonts lived in groups, with fossil sites showing multiple individuals buried together, possibly families or herds. This was not a simple, primitive world. The animals of Pangaea were sophisticated, adapted to their environments, engaged in complex interactions. Predator and prey co-evolved, each driving the other toward greater speed, strength, and cunning. Herbivores developed defenses, size, armor, social cohesion. Carnivores developed strategies, stealth, speed, pack hunting. The ecosystems functioned much as modern ecosystems do, with energy flowing from plants to herbivores to carnivores, with decomposers breaking down the dead and returning nutrients to the soil. And these animals were not static. Over tens of millions of years, they evolved. Body plans shifted. Metabolic rates increased. Brains grew larger. Sensory systems became more acute. Social structures became more elaborate. The trajectory was clear. Synapsids were moving toward greater complexity, toward the traits we associate with intelligence. By the late Permian, synodonts possessed many of the physical prerequisites for higher cognition. Warm-bloodedness provided the energy budget for larger brains. Differentiated teeth and complex jaws allowed for diverse diets, reducing the risk of starvation and freeing time for activities beyond foraging. Whiskers suggested heightened sensory awareness. Social behavior implied communication and cooperation. Relative brain size, while not as large as in later mammals, was increasing. Did intelligence emerge among the synapsids of Pangaea? Did any species cross the threshold from instinct-driven behavior to something we would recognize as thought, planning, problem-solving? Did they develop culture, technology, language? We don't know. The fossil record provides bones, teeth, and occasional impressions of skin or fur. It does not preserve behavior, cognition, or social structure except in the crudest outlines. We can infer much from anatomy, brain size, sensory organs, limb structure, but inference has limits. A large brain suggests potential for intelligence, but it does not prove intelligence. Social behavior indicates cooperation, but not necessarily abstract thought. What we can say is this: the rulers of Pangaea were sophisticated, successful, and evolving toward traits associated with intelligence. They dominated the land for over 100 million years, a span of time far longer than mammals have held dominance in the post-dinosaur world. If intelligence was going to evolve anywhere, Pangaea's synapsids seem like plausible candidates. The question then is whether 160 million years, the full duration of Pangaea's existence, was enough time. Was it enough for a lineage of synapsids to evolve not just larger brains, but minds capable of abstract reasoning? Was it enough for tool use to develop, for culture to emerge, for a species to cross the line from animal to something more? And if it did happen, would we ever know? 160 million years. That's how long Pangaea existed as a unified landmass. For perspective, consider that the entire lineage leading from ape-like ancestors to modern humans spans roughly 6 million years. From Australopithecus to Homo sapiens, from the first crude stone tools to spacecraft and quantum computers, took 6 million years. Multiply that by 26 and you approach the duration of Pangaea's existence. 26 times the entire span of human evolution. 26 opportunities for a lineage to take a different path, to stumble upon the combination of traits that leads to intelligence, culture, and technology. The question is not whether there was enough time. There was. The question is whether the raw materials, the anatomical, physiological, and ecological conditions were present. Intelligence does not arise from nothing. It requires a constellation of factors, each necessary but none alone sufficient. The first is brain size, or more precisely, brain-to-body ratio. A large brain relative to body mass provides the neural substrate for complex cognition. Elephants have larger brains than humans in absolute terms, but humans have larger brains relative to their body size. This ratio, encephalization, correlates with problem-solving ability, memory, and behavioral flexibility across species. The second factor is energy. Brains are metabolically expensive. The human brain, accounting for roughly 2% of body mass, consumes about 20% of the body's energy budget. Sustaining a large brain requires a reliable food supply and an efficient metabolism. Warm-bloodedness, endothermy, helps by maintaining a constant internal temperature, allowing the brain to function optimally regardless of external conditions. Cold-blooded animals, whose metabolic rates fluctuate with temperature, struggle to support energy-hungry neural tissue. The third factor is social behavior. Intelligence evolves in a social context. Cooperation, communication, competition all drive the development of cognitive abilities. Animals that live in groups must navigate complex social hierarchies, remember individuals, anticipate behavior, and coordinate actions. Social species tend to be more intelligent than solitary ones. Primates, dolphins, elephants, and corvids, all highly social, rank among the most cognitively sophisticated animals. The fourth factor is physical capability. Intelligence is most useful when paired with the ability to manipulate the environment. Hands, trunks, tentacles, beaks, tools for grasping, probing, and reshaping the world. Primates have opposable thumbs. Elephants have trunks. Octopuses have tentacles. Crows have precise beaks. These appendages allow for tool use, a behavior strongly correlated with intelligence. Without the means to act on ideas, intelligence offers diminished evolutionary advantage. The fifth factor, often overlooked, is time. Evolution is not fast. Traits emerge through mutation, are tested by natural selection, and either persist or vanish. Accumulating the suite of traits required for intelligence takes millions of years. Hominins, the lineage including humans and our closest extinct relatives, spent roughly 6 million years evolving from Australopithecus afarensis to Homo sapiens. Even then, behavioral modernity, the full expression of human intelligence, including art, symbolic thought, and complex language, emerged only in the last 100,000 years or so. Given these prerequisites, how did the synapsids of Pangaea measure up? Brain size is difficult to assess directly. Brains do not fossilize, but brain cases do. By examining the internal volume of fossil skulls, paleontologists can estimate brain size. Late Permian cynodonts, particularly the more advanced species, had encephalization quotients, EQ, a measure of brain size relative to expected brain size for a given body mass, higher than earlier synapsids. They were not at modern mammalian levels, but they were trending in that direction. Cynodonts had larger brains than pelycosaurs, and within the cynodont lineage, later species had larger brains than earlier ones. Energy was less of a constraint. As discussed, many therapsids, including dicynodonts and cynodonts, were likely endothermic. Warm-bloodedness provided the metabolic foundation for supporting larger, more active brains. Cynodonts, in particular, with their differentiated teeth and efficient jaws, could process food quickly and extract maximum nutrition. This dietary efficiency freed time and energy for activities beyond mere survival: play, exploration, social interaction, behaviors associated with intelligence. Social behavior is harder to infer from fossils, but clues exist. Some dicynodont species have been found in mass graves, dozens of individuals buried together, suggesting they lived in groups. Trackways, fossilized footprints, sometimes show multiple animals moving in the same direction, possibly indicating herding or pack behavior. Gorgonopsians, apex predators, may have hunted cooperatively, though direct evidence is lacking. Cynodonts, given their mammalian affinities, likely exhibited complex social structures similar to those seen in modern social mammals. Physical capability is where the picture becomes more ambiguous. Synapsids had 4 limbs, each with 5 digits. Early synapsids, like Dimetrodon, had sprawling limbs poorly suited for manipulation. Therapsids improved, with limbs positioned more directly beneath the body, but their forelimbs were still primarily for locomotion. Cynodonts, being small and agile, may have used their forepaws for digging, grasping prey, or manipulating objects to a limited degree, but they lacked the opposable thumbs or prehensile appendages that characterize tool-using species today. This is a significant limitation. Tool use, as far as we know, requires appendages specialized for manipulation. Primates evolved opposable thumbs. Elephants evolved trunks. Octopuses evolved tentacles with fine motor control. Crows evolved precise beaks and feet capable of holding objects. Without analogous structures, tool use is difficult. Synapsids, despite their many advances, retained a basic tetrapod body plan optimized for walking and running, not for delicate manipulation. That said, the absence of tool-using adaptations does not preclude intelligence. Dolphins are highly intelligent, with complex social structures, communication systems, and problem-solving abilities, yet they lack hands or any means to create tools. Their intelligence evolved in a different context, driven by social complexity rather than environmental manipulation. Intelligence does not have a single path. It can emerge in response to different selection pressures. Time, as already established, was not a limiting factor. 160 million years is vastly more than evolution needs to produce intelligence, assuming the other prerequisites are met. The mammalian lineage, from the first small mammals in the Triassic to humans today, spans roughly 200 million years, and intelligence emerged in just the last fraction of that time. If synodonts had continued evolving uninterrupted, there is no reason, in principle, that intelligence couldn't have arisen within the span of Pangea's existence. The counter-arguments are straightforward. First, brain size. Even the largest-brained synodonts had brains smaller than those of early hominins. Australopithecus had a brain volume of roughly 400 to 500 cubic centimeters. Early Homo species ranged from 600 to 900 cubic centimeters. Modern humans average 1,300 to 1,500 cubic centimeters. Synodonts, by comparison, had brains measured in tens of cubic centimeters at most. This is a significant gap. Second, there is no fossil evidence of tool use. Stone tools leave marks on bones, cut marks from butchery, percussion marks from breaking open bones for marrow. No Permian fossils show such marks. No caches of worked stone have been found in Permian deposits. No modified bones, no shaped sticks, no evidence that any synapsid ever crafted a tool. Third, there is no evidence of controlled fire. Fire is a hallmark of human intelligence used for cooking, warmth, protection, and light. Controlled fire leaves traces, charcoal layers, scorched earth, fire-cracked rocks. No such evidence exists in Permian strata. If a civilization arose on Pangaea, they either did not use fire or left no detectable traces. These are serious objections. However, they come with caveats. Brain size is not a perfect predictor of intelligence. Modern crows have brains weighing 15 grams, smaller than a walnut, yet they use tools, solve multi-step problems, recognize faces, and demonstrate insight learning. Octopuses have brains spread throughout their bodies, with much of their neural processing occurring in their arms, yet they are among the most intelligent invertebrates, capable of complex problem-solving and learning by observation. Parrots, with brains the size of a shelled walnut, can understand abstract concepts and use language meaningfully. Intelligence, it turns out, is not just about size, it's about organization, connectivity, neural density. A small brain wired efficiently can outperform a larger brain wired poorly. The human brain's power comes not just from its size, but from the density of its neurons, the complexity of its synaptic connections, and the specialization of its regions. If synodonts evolved brains with similar organizational efficiency, their smaller absolute size might not have been a limiting factor. Tool use, likewise, is not the only marker of intelligence. Dolphins don't use tools but pass down cultural knowledge, hunting techniques specific to individual pods, taught from generation to generation. Elephants recognize themselves in mirrors, mourn their dead, and cooperate in complex tasks without ever manipulating objects in the way primates do. Intelligence can manifest in forms that don't leave archaeological traces. Fire is perhaps the strongest argument against a Pangean civilization. Fire is so useful, so transformative, that it's hard to imagine any intelligent species not discovering it. Yet the absence of evidence is not conclusive. Controlled fire might have been used sparingly in locations not preserved in the fossil record. Or perhaps the Permian atmosphere, with different oxygen levels, affected combustion in ways we don't fully understand. Or perhaps intelligence arose in a form that simply didn't rely on fire. A coastal, maritime culture, for instance, where raw food from the ocean was abundant. The deepest problem is that behavior does not fossilize. Bones preserve, teeth preserve. Occasionally, skin or even fur impressions preserve. Behavior, cognition, culture, these leave almost no direct trace. We infer social structures from trackways and mass burials. We infer diet from toothware and coprolites. We infer locomotion from limb proportions. But thought, language, abstract reasoning, symbolic expression, these are invisible in the fossil record unless they produce physical artifacts. If a species of cynodont evolved intelligence, developed language, formed complex societies, but never made stone tools, never lit fires, never built structures that could survive 250 million years of erosion and subduction, we would have no way to detect them. They would be ghosts, present in the evolutionary timeline, but invisible to paleontology. This brings us back to the central question: could synapsids have evolved intelligence? The answer, frustratingly, is maybe. They had many of the prerequisites: endothermy, increasing brain size, social behavior, vast stretches of time. They lacked others: tool-using appendages, clear evidence of environmental manipulation. The gap is not impossible to bridge, but it's significant. What we can say with certainty is that if intelligence did arise among Pangea's synapsids, it would not have looked like human intelligence. It would have emerged from a different body plan, adapted to different ecological pressures, expressed in ways we might not recognize. It might have been social and linguistic, but non-technological. It might have been sophisticated, but left no material culture. It might have thrived for millions of years and then vanished in the Great Dying, leaving behind nothing but bones we've misinterpreted as those of animals. And that leads to the next question. If they did exist, what would their civilization have looked like? First, set aside your assumptions. A civilization on Pangaea would not have resembled ours. There would be no cities of steel and glass, no highways cutting through landscapes, no smokestacks or power lines or satellites. Those trappings of modernity arose from specific historical circumstances: the discovery of fossil fuels, the development of metallurgy, the accumulation of scientific knowledge over generations. A civilization arising 250 million years ago, built by creatures with different anatomies and different ecological pressures, would have followed a different path entirely. Consider the body plan. Synapsids, even the most advanced cynodonts, lacked hands. They had forelimbs with 5 digits, but these were primarily for locomotion, running, climbing, digging, not for fine manipulation. Without opposable thumbs or prehensile appendages, tool use would have been limited. They might have fashioned crude implements from bone or stone, held awkwardly in their jaws or braced against the ground, but they could not have crafted the precision tools that define human technology. No needles, no pottery wheels, no metal forges. Their technology, if it existed, would have been fundamentally constrained by anatomy. This means their civilization, if it arose, would have been pre-industrial. Not primitive. Sophistication and industrialization are not the same thing, but limited in the materials they could work and the structures they could build. Stone, wood, bone, perhaps perhaps plant fibers woven into cords or mats. Simple tools shaped by abrading one material against another. Shelters built from branches, leaves and hides. Nothing that would survive 250 million years of weathering, erosion and tectonic upheaval. Where would such a civilization have emerged? Almost certainly on the coasts. Pangea's interior was harsh, vast deserts with extreme temperatures and little water. The coasts, by contrast, were productive. Rivers delivered nutrients from the highlands, creating rich estuaries and deltas. The ocean provided food, fish, shellfish, marine invertebrates. Coastal regions experienced monsoons, meaning seasonal but reliable rainfall. Forests grew near the water's edge. Resources were abundant and the climate was moderate compared to the scorching or freezing interior. A coastal civilization would have been maritime. Pangea's coastline stretched for tens of thousands of kilometers. The Tethys Sea alone was vast, and Panthalarsa's shores extended even farther. If an intelligent species arose on one part of the coast, they might have eventually spread along the shoreline, following the water, settling in river mouths and protected bays. They might have developed boats, simple rafts or dugout canoes, to cross estuaries or explore nearby islands. Watercraft, like all organic materials, would rot away entirely within centuries, leaving no trace. Communication would likely have been oral. Language does not require writing. Aboriginal Australians preserved complex knowledge systems for 65,000 years without ever developing a written script. Their oral traditions encoded astronomy, ecology, law and history, passed down through song, story and ritual. A Pangean civilization could have done the same. They might have had rich mythologies, intricate social structures, and detailed knowledge of their environment, all transmitted verbally from generation to generation. None of this would fossilize. Art, if it existed, would have been ephemeral. Body paint made from crushed minerals or plant dyes, applied during ceremonies. Carvings in wood, which would decay. Patterns drawn in sand or mud, erased by the next tide or rainstorm. Symbolic markings on rocks might survive longer, but after 250 million years, even petroglyphs would weather away. The stone itself would erode, taking any engravings with it. Architecture would have been modest. No pyramids, no temples of stone blocks fitted with precision. Perhaps simple structures, wooden poles driven into the ground, supporting roofs of woven reeds or animal hides. Windbreaks, fish weirs, corrals for containing captured animals. These would leave, at best, post holes or shallow depressions in the ground, features easily obliterated by sedimentation, erosion, or tectonic activity. Even if preserved, they would be ambiguous, difficult to distinguish from natural formations. Paths and roads, if they existed, would have been dirt tracks, worn down by repeated passage. In a pre-industrial society without wheels or beasts of burden, there would be little need for paved roads. Footpaths through forests, along coastlines, across plains, these would vanish quickly after abandonment, reclaimed by vegetation or eroded by rain. In 250 million years, not a trace would remain. Fire, as discussed, is a problem. Controlled fire leaves evidence: charcoal layers, heat-altered soils, fire-cracked rocks. The absence of such evidence in Permian strata is conspicuous. One possibility is that a Pangean civilization never discovered fire, relying instead on raw food from the ocean and plants. Another possibility is that they used fire sparingly in locations not represented in the fossil record, coastal areas that were later subducted or eroded. A third possibility is that we're looking in the wrong places or with insufficient resolution to detect isolated hearths from such deep time. The point is this: a civilization that never industrialized, that built with organic materials, that communicated orally, that lived along coastlines now submerged or scattered across continents, such a civilization would be invisible to us, not because they were unsophisticated, but because their sophistication left no durable record. History provides instructive parallels. Göbekli Tepe in modern-day Turkey is a temple complex built roughly 11,000 years ago by people who had not yet domesticated plants or animals. They were hunter-gatherers, yet they quarried, transported and erected massive stone pillars, some weighing 10 tons, carved with intricate reliefs of animals. The site required planning, organization, and sustained effort across generations. It defies the stereotype of Neolithic peoples as simple and unsophisticated. Aboriginal Australians, as mentioned, maintained a continuous culture for at least 65,000 years, possibly longer. They developed complex fire management techniques, transforming landscapes to encourage the growth of desired plants. They created sophisticated kinship systems, trade networks spanning thousands of kilometers, and oral traditions encoding astronomical knowledge that has been verified by modern science. They did all this without agriculture, without metal tools, without writing. To an archaeologist from a distant future who encountered only their stone tools and middens, they might appear primitive. The reality is far richer. Polynesian navigators crossed the Pacific Ocean in outrigger canoes, colonizing islands thousands of kilometers apart, using only observations of stars, waves, and birds to guide them. They had no maps, no compasses, no written records. The knowledge was passed down orally, encoded in chants and memorized navigation techniques. This is sophisticated technology, just not the kind that leaves an archaeological footprint. The bias, then, is ours. We equate civilization with cities, writing, and metal. We assume intelligence manifests in ways that produce durable artifacts. A culture that lives lightly on the land, that builds with perishable materials, that relies on memory rather than text. Such a culture can be sophisticated, intelligent, and entirely invisible to future paleontologists. A Pangean civilization, if it existed, would likely have been invisible in precisely this way. They might have had language, culture, social hierarchies, art, and technology, all adapted to their environment and anatomy. They might have thrived for millions of years, spreading along coastlines, adapting to climate shifts, passing down knowledge through oral traditions. And when the Permian Triassic extinction arrived, they would have perished, leaving behind nothing we could recognize as evidence. Their bones, if fossilized, would look like the bones of animals. No tools clutched in hand, because there were no hands. No grave goods, because burial rituals, if they existed, might not have included objects. No structures, because wood and fiber decay. No fire pits, because fire use was absent or rare or confined to locations now destroyed. Just bones, teeth, scattered fragments in sediment layers, indistinguishable from any other synapsid that lived and died on Pangaea. And yet, absence of evidence is not evidence of absence. The fossil record is profoundly incomplete. Most organisms never fossilize, most behaviors leave no trace, most environments are poorly sampled. The idea that we would definitively detect a pre-industrial, coastal, orally transmitted civilization from 250 million years ago is, frankly, hubris. This raises a final question, one that extends beyond the boundaries of Earth. If a civilization could exist and leave no trace on its home planet, what about the Moon, or Mars, or other celestial bodies where erosion and plate tectonics are absent or minimal? If Pangea's synapsids achieved spaceflight, an admittedly wild speculation, could evidence of their existence survive there, where Earth has erased it? That is the question we turn to next. The idea sounds absurd on its face. Synapsids, creatures with no hands, limited tool use, and, at best, pre-industrial technology, somehow developing spaceflight and leaving artifacts on the Moon or Mars. It reads like science fiction, a premise too outlandish to take seriously. And yet, when Frank and Schmidt published the Silurian Hypothesis, they included a brief discussion of this very possibility. Not because they believed it happened, but because the logic is sound. If you're searching for traces of an ancient civilization, space is a better archive than Earth. The reasoning is straightforward. Earth is geologically active. Plate tectonics recycles the crust. Erosion wears down mountains. Wind and water reshape landscapes. Biological processes decompose organic matter. Over 250 million years, these forces erase almost everything. The Moon, by contrast, has no plate tectonics. It has no atmosphere to speak of, so there's no wind or rain. It has no life to break down materials. Once something lands on the Moon's surface, it stays there, largely undisturbed, for billions of years. Mars falls somewhere in between. It has a thin atmosphere, so there is wind and occasional dust storms that can bury or erode features. It has no active plate tectonics, though it may have had tectonic activity in the distant past. Water once flowed on Mars's surface, carving channels and depositing sediments, but that was billions of years ago. Today, Mars is cold, dry, and geologically quiet. Artifacts left on its surface millions of years ago would be weathered by dust and radiation, but they would not be obliterated the way they would be on Earth. If an ancient civilization achieved spaceflight, if they built rockets or spacecraft capable of reaching the Moon or Mars, and if they left behind bases, tools, or debris, those remnants could still be there, waiting to be discovered. This is not idle speculation. It's a testable hypothesis. We have sent probes to the Moon and Mars. We have orbited them with high-resolution cameras. We have walked on the Moon and driven rovers across Mars. If there were obvious signs of ancient construction, ruins, landing pads, large-scale structures, we would have seen them by now. We haven't. The Apollo missions returned roughly 380 kilograms of lunar rock and soil, meticulously analyzed for decades. No manufactured objects, no anomalous materials. The Lunar Reconnaissance Orbiter, which has been mapping the Moon since 2009, has imaged nearly the entire surface at resolutions high enough to spot the abandoned Apollo landers and rover tracks. No ancient artifacts, no mysterious structures, just craters, plains, and the scars of billions of years of meteorite impacts. Mars has been explored by orbiters, landers, and rovers for decades. Cameras have mapped the surface in extraordinary detail. Rovers have driven across ancient lake beds, climbed mountains, and drilled into rocks. The data is rich, revealing a planet that once had liquid water, a thicker atmosphere, and possibly conditions suitable for life. There is no sign, however, of artificial structures, no evidence of past industrial activity, no relics of a civilization. Does this mean a Pangean civilization never went to space? Not necessarily. The absence of evidence, once again, is not conclusive. First, we've only scratched the surface, literally. The Moon's surface area is roughly 38 million square kilometers, about the size of Africa and Europe combined. The Apollo missions explored 6 sites, each covering a few square kilometers. The rovers and landers that have visited the Moon since have added a few more data points, but the total area directly examined by humans or robots is a minuscule fraction of the whole. Most of the Moon remains unvisited, observed only from orbit. Orbital imaging can detect large features, craters, boulders, anything more than a meter or so across, but small objects are invisible. A collapsed outpost buried under lunar regolith by billions of years of micrometeorite bombardment would be undetectable unless you happen to dig in exactly the right spot. Footprints, tools, small debris, these would require surface exploration to find, and we've barely begun that process. Mars is even less explored. Its surface area is roughly 145 million square kilometers, nearly the same as all of Earth's land area. Rovers have covered, in total, a few dozen kilometers of driving distance. That's the equivalent of exploring Earth by driving a single car from New York to Philadelphia and declaring, based on that journey, that no evidence of ancient civilizations exists anywhere on the planet. The comparison is not perfect. Orbital imaging helps, but it illustrates the scale of the problem. Mars is vast. Our exploration has been limited. Second, even if artifacts exist, they might be buried. The Moon's surface is constantly being gardened by micrometeorite impacts, a process that mixes and buries material over time. The top few meters of lunar regolith have been churned and reworked over billions of years. Something left on the surface 250 million years ago would likely be buried under a layer of dust and broken rock. Finding it would require excavation, not just observation. Mars has dust storms that can blanket the entire planet, depositing layers of fine sediment. Ancient structures or artifacts could be buried under meters of dust, invisible to surface rovers or orbital cameras. The Martian polar ice caps, which advance and retreat over long timescales, could also conceal objects beneath layers of ice and dust. Third, there's the question of what we're looking for. If a civilization did go to space, what would they leave behind? Human spaceflight has produced landing modules, rovers, flags, footprints, and discarded equipment. These are detectable because they're recent and because we know where to look. A spacefaring synapsid civilization, 250 million years ago, would have left very different traces. Their technology would be unrecognizable. Their materials might not stand out from natural features. Their bases, if they built any, might resemble geological formations more than structures. Without knowing what to look for or where, the search becomes impossibly broad. Anomalies detected by orbiters, unusual rock formations, odd color patterns, peculiar shapes, are almost always explained by natural processes once examined up close. The face on Mars, famously photographed by Viking 1 in 1976, turned out to be a mesa, a trick of light and shadow. The pyramids of Cydonia are hills. The monolith, discovered by Phobos 2, is a boulder. Pareidolia, the tendency to see patterns where none exist, plagues the search for extraterrestrial artifacts. All of this assumes, of course, that a Pangean civilization achieved spaceflight in the first place. This is where the hypothesis becomes strained. Spaceflight requires a cascade of technological developments: metallurgy, chemistry, engineering, precision manufacturing, mathematics, physics. It requires harnessing energy on a massive scale, fossil fuels, nuclear power, or some other concentrated energy source. It requires written knowledge, because the complexity of rocketry cannot be transmitted orally. It requires infrastructure, factories, launch pads, supply chains. A pre-industrial, orally transmitted coastal culture without hands, without metal tools, without writing. Such a culture achieving spaceflight strains credulity. It's not impossible in some abstract theoretical sense, but it requires such a radical departure from anything we understand about technological development that it enters the realm of pure fantasy. The most likely scenario is that they never left Earth. If an intelligent species arose on Pangaea, they lived, thrived for a time, and then perished in the Great Dying, never achieving the technological sophistication required for spaceflight. Their story began and ended on this planet. The evidence, if it ever existed, is here. Erased by time, buried under sediment, subducted into the mantle, or weathered into dust. The space preservation theory, then, is more useful as a thought experiment than as a serious avenue of investigation. It forces us to think about what traces civilizations leave how long those traces persist, and what tools we'd need to detect them. It highlights the limits of our current exploration and the vastness of what remains unknown. It reminds us that absence of evidence, while suggestive, is not proof. If we ever do find ancient artifacts on the Moon or Mars, they're more likely to belong to some other species entirely, an extraterrestrial civilization that visited our solar system millions of years ago and left souvenirs. That would be a discovery for the ages, unrelated to Pangaea, but no less profound. For now, though, the Moon is silent. Mars is barren. And if Pangea's synapsids ever looked up at the stars and wondered, as we do, whether they were alone, they never learned the answer by going there. Which brings us back to Earth, to the deeper question underlying this entire investigation. Why do we assume we're the first? Why does the idea of a previous civilization feel so foreign, so unsettling? The answer lies not in geology or paleontology, but in psychology. It lies in how we think about ourselves, our place in history, and the nature of intelligence itself. We are, by nature, the center of our own universe. This is not arrogance, it's neurological inevitability. Our brains construct reality from the narrow slice of sensory input available to us. We experience time linearly, from birth to death, measured in decades. We experience space locally, within the bubble of places we can reach in a lifetime. And we experience history through the lens of recorded knowledge, stretching back, at most, a few thousand years. This perspective creates blind spots. One of the deepest is our assumption of uniqueness. We believe almost instinctively that intelligence is rare, that consciousness is a recent phenomenon, that civilization, in any meaningful sense, began with us, with agriculture, writing, cities, industry. The narrative we've constructed places humanity at the apex of a long, progressive arc, simple to complex, primitive to advanced, animal to human. But this narrative is built on a foundation of temporal myopia. We forget how old the Earth is. We forget how long life has existed. We forget that complex organisms have been evolving, adapting, and thriving for hundreds of millions of years before the first human ancestor climbed down from a tree. Consider the numbers. Anatomically modern humans, Homo sapiens, emerged roughly 300,000 years ago. For most of that time, we lived in small bands, hunting and gathering, with technologies that would be unrecognizable to anyone living today. Fire, stone tools, basic shelters. Agriculture appeared around 12,000 years ago, a blink of an eye in evolutionary time. Writing emerged 5,000 years ago. Industrialization, the explosion of technology, science, and culture that defines the modern world, began roughly 300 years ago. 300 years, that's all. Less than the lifespan of a single Galapagos tortoise. 1/4000th of the time Homo sapiens has existed. 1/1,000,000th of the time since Pangaea formed. Now consider Pangaea. It existed for 160 million years. Multiply the entire span of human existence from the first Homo sapiens to today by more than 500, and you approach the duration of that supercontinent. Multiply the span of human industrial civilization, the age of machines, electricity, computers, by more than 500,000, and you're in the same ballpark. 500,000 times longer. That's not just a difference in scale, it's a difference in kind. It's the difference between a heartbeat and an eon. If a civilization arose on Pangaea and lasted 10 million years, a modest span by geological standards, that would be 33,000 times longer than our industrial age. 33,000 industrial revolutions, back to back, and you'd still have millions of years left over. This is the first bias, temporal. We think in human timescales, and those timescales are minuscule compared to the age of the planet. When we imagine ancient, we think of Egypt, Mesopotamia, maybe the Ice Age. 10,000 years feels like deep time. But 10,000 years is nothing. It's a rounding error in geological history. The Earth doesn't notice decades. It barely notices millennia. The second bias is definitional. We define civilization by our own metrics: cities, writing, metal, industry. We assume that intelligence manifests in ways that produce durable artifacts, that cultures progress along a similar trajectory to our own, that the markers we value are universal markers. They are not. Civilization is not a single path. It's a space of possibilities, and we've explored only a narrow corner of it. Aboriginal Australians maintained a continuous culture for at least 65,000 years without developing agriculture, metallurgy, or writing. Their knowledge systems were encoded in oral traditions, their histories preserved in song and story, their technologies adapted to the environments they inhabited. By the standards of industrial Europe, they might have appeared primitive. In reality, they were supremely adapted, having outlasted every empire, every dynasty, every advanced civilization that rose and fell in Eurasia over the same span. Göbekli Tepe, as mentioned, defies the conventional timeline. Hunter-gatherers, who supposedly lacked the organization and surplus resources required for monumental architecture, built a temple complex that required quarrying, transporting, and erecting multi-ton stone pillars. They did this 11,000 years ago, before the invention of pottery, before the domestication of plants. The site suggests that our assumptions about the sequence of technological development, agriculture, then cities, then monuments, are overly simplistic. Complexity can arise in unexpected ways. The third bias is biological. We assume intelligence is rare because we see only one example: us. Every other species on Earth, no matter how sophisticated its behavior, falls short of human-level cognition. Chimpanzees use tools but don't build cities. Dolphins communicate but don't write. Crows solve problems but don't develop science. From this, we conclude that the leap to intelligence is difficult, improbable, perhaps unique. This conclusion is premature. Intelligence, as we've discussed, is not a single trait. It's a constellation of abilities: memory, problem-solving, social cognition, communication, abstraction, that can be assembled in different ways. Crows are intelligent in ways that differ from octopuses. Elephants are intelligent in ways that differ from dolphins. Humans are intelligent in ways that differ from all of them. If we're looking for human intelligence in non-human species, of course we won't find it. But that doesn't mean other forms of intelligence don't exist, or couldn't have existed in the past. The fourth bias is evidential. We assume that if intelligence had arisen before, we would find evidence: stone tools, fire pits, structures, fossils with enlarged brain cases. The absence of such evidence is taken as proof that no prior intelligence existed. But this assumes the fossil record is complete or even representative. It is neither. The fossil record captures, at best, a tiny fraction of the organisms that have ever lived. Most species leave no fossils. Most individuals within a species leave no fossils. Most environments are poorly sampled. Coastal regions where a pre-industrial civilization would most likely have thrived are now underwater or have been subducted. Organic materials, wood, fiber, skin, decay within years or decades. Bones fossilize only under specific conditions, and even then they're often crushed, scattered, or destroyed by subsequent geological processes. If a civilization existed on Pangaea, used organic tools, lived along coastlines, transmitted knowledge orally, and left no metal or writing, if that civilization was erased by the Permian Triassic extinction and then had its remains ground into dust by 250 million years of tectonics and erosion, the absence of evidence would be expected, not surprising. And yet, we interpret absence as proof. This is the evidential bias, confusing "we haven't found it" with "it doesn't exist." The distinction matters. One is a statement about our search efforts. The other is a statement about reality. They are not the same. The final bias is existential. The idea that we might not be the first intelligent species on Earth is unsettling. It undermines our sense of specialness, our place at the center of the story. If intelligence has arisen before, if civilizations have come and gone, if the experiment has been tried and failed multiple times, then we are not unique. We are not the chosen ones, the culmination of evolution, the pinnacle of progress. We are just the latest iteration, one more attempt in a long series, with no guarantee that we'll fare better than our predecessors. This is uncomfortable. It forces humility. It demands that we see ourselves not as the end point of history, but as a waypoint, a fleeting moment in a process vastly larger and older than we are. It suggests that the universe does not revolve around us, that our achievements, impressive as they seem, are temporary, that our legacy may be as invisible to future geologists as Pangea's hypothetical civilization is to us. And perhaps that's the deepest reason we resist the idea. Not because the evidence rules it out, it doesn't, but because accepting it changes how we see ourselves. It strips away the myth of exceptionalism and replaces it with the cold, indifferent reality of deep time. Intelligence may not be rare. It may arise whenever conditions permit, flourishing for a time before being cut short by extinction, environmental collapse, or some other catastrophe. The rarity is not intelligence itself, but the preservation of its traces. Civilizations are ephemeral. Earth is patient. Given enough time, the planet erases everything. If that's true, then the question is not whether a civilization existed before us. The question is whether we will leave traces that endure, or whether we too will vanish into the geological record, reduced to an ambiguous layer of sediment that future paleontologists puzzle over and dismiss. And that brings us to the present, to us, to the choices we're making, the marks we're leaving, and the future we're shaping. Because if Pangea's story teaches us anything, it's this. The Earth has seen civilizations rise and fall before, and it will see them again. The only question is whether we'll be one of the ones remembered, or one of the ones forgotten. We are, in all likelihood, leaving behind exactly the kind of civilization that would be invisible in 250 million years. This is not speculation. It's a conclusion that follows directly from the Silurian Hypothesis. When Frank and Schmidt asked what traces an industrial civilization would leave, they were not thinking abstractly. They were thinking about us, about the markers of the Anthropocene, the proposed geological epoch defined by human impact on Earth's systems, and whether those markers would persist over geological time. The answer, they found, was unsettling. Most of what we consider permanent, our cities, our infrastructure, our monuments, will not survive. Steel corrodes, concrete crumbles, glass weathers into sand, plastics degrade chemically, breaking down into smaller and smaller fragments until they become part of the sediment, indistinguishable from organic residues. Over millions of years, even these traces fade. Over tens of millions, almost nothing remains visible. What persists are the signatures we've discussed. Geochemical anomalies, a spike in light carbon isotopes marking the burning of fossil fuels, elevated concentrations of plutonium-244 and other synthetic radioisotopes, remnants of nuclear weapons testing and reactor accidents, unusual distributions of nitrogen and phosphorus, the fingerprints of industrial agriculture, elevated levels of lead, mercury, and other heavy metals spread globally by industry and mining, a sharp increase in extinction rates, the biological signal of habitat destruction and climate disruption. These are the markers of the Anthropocene, and in 250 million years, after plate tectonics has subducted much of the current sea floor, after erosion has worn down today's mountains, after ice ages and supercontinent cycles have reshaped the continents. These markers may be all that remains. Future geologists might find a thin layer of sediment with anomalous chemistry, debate its origins, and conclude it could be explained by volcanism, asteroid impacts, or some other natural event. They might never know a civilization caused it. This is the mirror. We look back at Pangaea and wonder whether an intelligent species lived there, left no traces we can find, and vanished into the geological record. We look forward and realize we are that species. Not to Pangea's hypothetical inhabitants, but to whatever intelligence arises in the distant future, long after we're gone. The parallels to the Permian Triassic extinction are particularly striking. That event, as discussed, was triggered primarily by the Siberian Traps volcanism, which released massive amounts of carbon dioxide and sulfur dioxide into the atmosphere. The result was rapid global warming, ocean acidification, anoxia, and mass extinction. Roughly 70% of terrestrial species and 96% of marine species died. We are doing something remarkably similar. Since the Industrial Revolution, humans have burned trillions of tons of fossil fuels, coal, oil, natural gas, releasing carbon dioxide that had been locked underground for hundreds of millions of years. Atmospheric CO2 levels have risen from roughly 280 parts per million in pre-industrial times to over 420 parts per million today. This is the fastest increase in atmospheric carbon in at least 66 million years since the asteroid that killed the dinosaurs. The effects mirror those of the Permian extinction. Global temperatures are rising, ice sheets are melting, sea levels are climbing, ocean chemistry is shifting toward acidity, threatening calcifying organisms like corals and shellfish. Weather patterns are destabilizing, ecosystems are collapsing, species extinction rates are accelerating, with current estimates suggesting we're losing species at roughly 100 to 1,000 times the natural background rate. Some biologists argue we're in the early stages of the sixth mass extinction, comparable in scale to the previous 5, including the Permian event. The difference, of course, is that the Siberian Traps erupted for geological reasons beyond any species' control. We are choosing this. We know the consequences. We have the data, the models, the scientific consensus. And yet, the trajectory continues. There is a grim irony in this. If a civilization existed on Pangaea, it was destroyed by an extinction event caused by volcanism and climate disruption. If a civilization arises in the distant future and looks back at us, they will see we were destroyed, or at least profoundly diminished, by an extinction event caused by our own activity. Different mechanisms, same result. The specifics change. The pattern repeats. This is not to say we are doomed. The Permian extinction unfolded over tens of thousands of years. Ours is unfolding over centuries, which means it's also happening fast enough that we can, in theory, alter the outcome. We have awareness, we have agency, we can change course if we choose to. Whether we will is another question. The Anthropocene markers also raise a philosophical question. What do we want to leave behind? If our industrial signatures persist as geochemical anomalies, what story do they tell? That we harnessed energy, built cities, sent spacecraft to other worlds, or that we burned through Earth's fossil fuel reserves in 3 centuries, destabilized the climate, triggered a mass extinction, and vanished before we learned to live sustainably. The latter narrative seems more likely to survive. The technological achievements, satellites, computers, art, literature, science, will erode or decay. The ecological damage will persist as chemical signals in the rock. Future geologists, if they exist, will see the extinction layer, the carbon spike, the isotope anomalies. They may infer an intelligent cause, but they'll have no context. no knowledge of Shakespeare, no record of lunar landings, no understanding of quantum mechanics. Just a thin band of sediment with strange chemistry and a lot of missing species. This is the price of invisibility, not the absence of achievement, but the absence of preservation. We are building wonders, creating knowledge, pushing the boundaries of what intelligence can accomplish. None of it will survive in recognizable form. In 250 million years, we will be at best a mystery, a geochemical anomaly that future scientists puzzle over and debate, never quite able to prove what happened. Unless, of course, we find a way to make our presence unambiguous. Stone monuments erode, metal corrodes, digital storage degrades, but some materials persist longer than others. Ceramics can survive for millions of years. Certain isotopes remain detectable for tens of millions. Engraved information on durable substrates, tungsten, sapphire, fused quartz, could last even longer if placed in geologically stable locations and protected from erosion and subduction. There have been proposals for time capsules designed to communicate with distant futures, messages encoded in multiple languages, using universal symbols, sealed in durable containers and buried in cratonic shields, the ancient stable cores of continents that resist subduction. Whether such efforts would succeed is uncertain, but the impulse is understandable. We want to be remembered. We want our existence to mean something beyond the narrow span of our own lives. And yet, memory is not guaranteed. The Earth is indifferent. Time is vast. Civilizations rise, flourish, and fade. The geological record preserves some, erases others. There is no cosmic ledger keeping track of who came and went. No universal archive ensuring that every intelligent species is remembered. If Pangea's hypothetical civilization teaches us anything, it's this: existence is not enough. To be remembered, you must leave something that endures, and endurance in geological terms is harder than we think. So the question remains, will we be remembered? Or will we, like Pangea's synapsids, become a whisper in the rock, a faint chemical signature that future geologists notice, debate, and ultimately dismiss as just another natural fluctuation in a planet's long, turbulent history? The answer depends not on what we achieve, but on what we leave behind. And what we leave behind depends on the choices we make now. Let's be clear about something. The most likely scenario is that no industrial or technologically advanced civilization existed on Pangaea. The evidence, or rather the lack of it, points overwhelmingly toward this conclusion. While the Silurian Hypothesis demonstrates that detecting ancient civilizations is harder than we assume, absence of evidence still carries weight. And in this case, the absence is substantial. The strongest argument against a Pangean civilization is geochemical. If an industrial species had existed during the Permian period, burning fossil fuels at scale, manufacturing synthetic materials, or using nuclear energy, they would have left detectable chemical signatures. As discussed, these signatures include anomalous carbon isotope ratios, elevated levels of plutonium-244 and other long-lived radioisotopes, unusual concentrations of nitrogen and phosphorus from fertilizers, and elevated heavy metals from mining and industry. Geologists have studied Permian strata extensively, particularly the layers surrounding the Permian-Triassic extinction boundary. These rocks have been analyzed for chemical composition, isotopic signatures, and trace elements. The goal is typically to understand the causes and effects of the extinction, but the data would also reveal industrial markers if they existed. So far, no such markers have been found. The carbon isotope excursion at the extinction boundary can be explained by volcanic outgassing and the collapse of biological carbon cycling. The elevated sulfur and metal concentrations match volcanic signatures. There are no plutonium anomalies, no nitrogen spikes inconsistent with natural processes, No synthetic organic compounds. This is not definitive proof. It's possible we haven't sampled the right rocks, or that any signatures present are too faint to detect with current methods. But it's a significant strike against the hypothesis. Industrial civilizations leave large-scale chemical footprints. The fact that we don't see them in Permian rocks suggests strongly that no such civilization existed. The second argument is paleontological. The fossil record of Permian synapsids, while incomplete, shows a pattern of gradual evolutionary change. Pelycosaurs gave rise to therapsids. Therapsids diversified into multiple lineages: gorgonopsians, dicynodonts, cynodonts. Brain sizes increased incrementally. Locomotion became more efficient. Metabolic rates rose. There are no sudden jumps, no inexplicable leaps in complexity that would suggest artificial selection or some other non-evolutionary process. If a synapsid species had achieved intelligence and developed culture, we might expect to see its effects on other species, domesticated animals, for instance, or lineages that went extinct due to overhunting. We see none of that. The ecological patterns in the fossil record look like natural evolution and extinction, driven by environmental pressures and competition, not by the influence of an intelligent species reshaping its world. The third argument is anatomical. Cynodont brain sizes, while larger than earlier synapsids, were still small compared to those of intelligent species today. The largest cynodont brains may have been a few tens of cubic centimeters. Early hominins, Australopithecus, Homo habilis, had brains of 400 to 600 cubic centimeters. Modern humans average around 1300 to 1500. That's an order of magnitude difference. While brain size alone doesn't determine intelligence, it does set limits. A brain of 50 cubic centimeters simply does not have the neural mass to support the kind of abstract reasoning, long-term planning, and symbolic thought required for culture and technology. The fourth argument is artifactual. Despite decades of paleontological work in Permian deposits, no one has found unambiguous evidence of tool use. No stone tools, no bone tools, no worked materials, no structures, no fire pits. The absence is striking because even pre-industrial human cultures leave abundant evidence. Stone tools, once created, are nearly indestructible. They litter archaeological sites by the thousands. If synapsids had made stone tools for even a few thousand years, we should find them. We don't. The fifth argument is ecological. Fire, once controlled, spreads its use. Humans have used fire for at least 1 million years, possibly longer. Evidence of fire use appears not just at hearths, but in altered landscapes, forests burned to encourage new growth, savannas maintained by controlled burns. These practices leave widespread charcoal deposits, changes in plant community composition, and fire-adapted species. Permian strata show none of this. There are natural wildfires, of course, sparked by lightning or volcanic activity, but no pattern suggesting deliberate fire management. The sixth argument is philosophical, Occam's razor. The simplest explanation that accounts for the evidence is usually correct. The evidence we have, fossils of synapsids with gradually increasing brain sizes, no tools, no fire, no geochemical anomalies, is entirely consistent with a world inhabited by animals. Complex, sophisticated animals, certainly, but animals nonetheless. Adding a hypothetical intelligent civilization to the picture doesn't explain anything we observe. It only introduces complications. Taken together, these arguments are formidable. They don't prove a Pangean civilization is impossible, but they make it highly improbable. The weight of evidence tilts decisively toward the conclusion that synapsids, despite their many evolutionary innovations, never crossed the threshold into intelligence as we define it. Does this mean the question was pointless? Not at all. The value of the Silurian hypothesis and the Pangean speculation it inspires is not in whether it's correct. It's in what it forces us to consider. It challenges our assumptions about how civilizations are detected, how intelligence evolves, and how much we can infer from incomplete records. It makes us think about deep time, about the limits of preservation, about the biases embedded in our search methods. For astrobiology, this has practical implications. If we can't detect an ancient industrial civilization on our own planet, if the traces would be too faint or too ambiguous after just a few million years, how will we detect one on an exoplanet? Current methods for identifying habitable worlds rely on atmospheric signatures: oxygen, methane, water vapor. These indicate life, possibly, but not necessarily intelligence. An industrial civilization would alter its atmosphere in detectable ways: elevated CO2, synthetic halocarbons, other pollutants, but only while the civilization is active. Once it collapses or transitions to sustainable technology, those signals fade. Within thousands of years, the atmosphere returns to a near-natural state. A million years later, it's as if the civilization never existed. This means we could be looking at dead civilizations without knowing it, planets that once hosted intelligence but now appear lifeless, or planets with pre-industrial intelligent species that we mistake for merely habitable because they lack the atmospheric signatures we're searching for. The Silurian Hypothesis teaches us to broaden our search criteria, to think beyond the obvious markers, to recognize that intelligence can be ephemeral and invisible. It also humbles us. The exercise of imagining a lost civilization on Pangaea reminds us that we are not necessarily unique, not necessarily the first, not necessarily the only. It places human history in the context of geological time, where 300,000 years is a blip and 300 years of industrial civilization is a microsecond. It forces us to confront the fragility of memory, the inevitability of erasure, and the possibility that everything we build will someday be forgotten. These are uncomfortable realizations, but they're valuable. They strip away hubris. They ground us in reality. They help us see ourselves not as the culmination of evolution, but as one experiment among many, still in progress, with no guarantee of success. So no, a Pangean civilization almost certainly didn't exist. The evidence is against it. The arguments are strong. But the question, could it have existed? Would we know if it did? Is worth asking. Not because it changes the past, but because it changes how we think about the present and the future. And that brings us to the final piece of the puzzle, the pattern. Because whether or not Pangaea hosted an intelligent species, the broader story remains the same. Life evolves, complexity increases, dominant lineages rise, extinctions wipe them out, and the cycle begins again. This has happened at least 5 times in Earth's history. Are we in the middle of the 6th? And if so, what comes next? The pattern is unmistakable once you see it. Life evolves complexity. A lineage rises to dominance, spreading across ecosystems, filling niches, adapting to every available environment. For tens of millions of years, sometimes over 100 million, they rule the planet. And then, abruptly, catastrophe strikes. Volcanism, asteroid impact, climate collapse. The dominant lineage is shattered. Most species vanish. Survivors cling to existence in scattered refugia. The world empties. And then, slowly, life rebuilds. New lineages emerge from the wreckage, radiating into the vacant niches left by the extinction. Complexity returns. Ecosystems stabilize. A new dominant group takes over. The cycle begins again. This has happened at least 5 times in the last 500 million years. 5 mass extinctions, each erasing the majority of species on Earth, each followed by a recovery that took millions of years. The pattern is so consistent that paleontologists have divided Earth's history into geological periods based largely on these extinction boundaries. The end of the Ordovician, The end of the Devonian, the end of the Permian, the end of the Triassic, the end of the Cretaceous. Each marks a reset, a point where the old world ended and a new one began. The first of the Big Five was the Ordovician Silurian extinction, roughly 443 million years ago. At the time, life was concentrated in the oceans. Complex land plants had not yet evolved, and terrestrial ecosystems were sparse. The extinction, caused by rapid climate shifts associated with glaciation, killed an estimated 86% of all species. Trilobites, which had dominated for over 100 million years, were devastated. They survived, barely, but never regained their former diversity. The second was the late Devonian extinction, a prolonged event spanning roughly 16 million years, from 375 to 359 million years ago. Multiple pulses of extinction, possibly triggered by volcanic activity, asteroid impacts and ocean anoxia, killed around 75% of species. Reef-building organisms, armored fish, and many marine invertebrates disappeared. Early forests on land were hit hard, with some plant lineages going extinct entirely. The third was the Permian Triassic extinction, the Great Dying, which we've already discussed at length. 252 million years ago, the world nearly ended. 96% of marine species and 70% of terrestrial vertebrates died. It was the closest life has ever come to total annihilation. Recovery took more than 10 million years. The fourth was the Triassic-Jurassic extinction, roughly 201 million years ago. Volcanism associated with the breakup of Pangaea released massive amounts of carbon dioxide, triggering global warming and ocean acidification. Around 80% of species vanished. Large herbivores and carnivores were hit particularly hard. The extinction cleared the way for dinosaurs, which had been minor players during the Triassic, to become the dominant land vertebrates. The fifth was the Cretaceous-Paleogene extinction 66 million years ago, caused by the impact of a 10-kilometer-wide asteroid near what is now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons, igniting wildfires, triggering tsunamis, and ejecting so much debris into the atmosphere that sunlight was blocked for months or years. Global temperatures plummeted, photosynthesis collapsed. Roughly 76% of species went extinct, including all non-avian dinosaurs. Mammals, small and largely nocturnal during the Mesozoic, inherited the Earth. 5 extinctions, 5 resets, and now possibly a 6th. The current extinction event is different from the others in one crucial respect. It's caused by a single species, us. Habitat destruction, driven by agriculture, urbanization, and deforestation, has eliminated vast swaths of wilderness. Climate change, driven by fossil fuel combustion, is altering ecosystems faster than species can adapt. Pollution, plastics, pesticides, industrial chemicals, is poisoning air, water, and soil. Overfishing has collapsed marine populations. Invasive species, spread by global trade, are overwhelming native ecosystems. The result is an extinction rate estimated at 100 to 1,000 times the natural background rate. Species that took millions of years to evolve are disappearing in decades. Biodiversity, the variety of life on Earth, is plummeting. Some scientists argue that we've already crossed the threshold into a mass extinction event comparable to the Big Five. Others say we're approaching that threshold but haven't crossed it yet. Either way, the trajectory is clear. If current trends continue, the 6th extinction will rival or exceed the worst events in Earth's history. And then what? If human civilization collapses, whether from climate catastrophe, resource depletion, war, pandemic, or some combination, what comes next? History suggests life will recover. It always has. After the Permian extinction, life clawed its way back over 10 million years. After the asteroid that killed the dinosaurs, mammals diversified and filled the vacated niches within 10 million years. The planet is resilient. Extinction wipes the slate clean, but it also creates opportunities. New lineages emerge. Evolution experiments with new body plans, new strategies, new solutions to survival. The world rebuilds itself, richer and stranger than before. But who or what inherits the Earth after us? If humans vanish, the most likely candidates for future dominance are the species already adapted to human-altered environments. Rats, pigeons, cockroaches, crows, raccoons. These are the generalists, the opportunists, the survivors. They thrive in disturbed habitats. They eat almost anything. They reproduce quickly. In the ecological vacuum left by human extinction, they would spread rapidly, diversifying into new forms as they adapt to newly available niches. Over millions of years, descendants of rats might evolve into large herbivores, occupying the roles once filled by deer and cattle. Descendants of crows might evolve into apex predators, their intelligence giving them an edge in hunting and strategy. Descendants of octopuses, already among the most intelligent invertebrates, might colonize coastal and freshwater environments, developing new forms of manipulation and communication. Would intelligence re-emerge? It's impossible to say, but the question is worth considering. Intelligence has evolved at least once on Earth, in us. Some argue it's evolved multiple times independently, in primates, in corvids, in cetaceans, in cephalopods. If intelligence arises relatively easily when conditions favor it, then it might emerge again in whatever lineage comes to dominate the post-human world. Alternatively, intelligence might be rare, a fluke, an evolutionary dead end that worked once but is difficult to replicate. The fact that only one species out of billions has developed technology and abstract reasoning could suggest that the leap from animal intelligence to human-level cognition is exceptionally difficult. Perhaps the right combination of traits, bipedalism, opposable thumbs, social cooperation, vocal flexibility, is unlikely to appear again. Perhaps intelligence, for all its advantages, is fragile and easily lost. The duration problem is also telling. Synapsids dominated for over 100 million years before giving way to dinosaurs. Dinosaurs dominated for 165 million years before the asteroid ended their reign. Mammals have dominated for 66 million years so far. Humans, by comparison, have existed for 300,000 years. Our industrial civilization is 300 years old. We are newcomers. We have barely begun. If intelligence is rare, and if civilizations are fragile, then the pattern makes sense. Life evolves complexity over vast timescales. Intelligence arises occasionally, perhaps many times, but it doesn't last. It burns bright and brief, then collapses, leaving only faint traces or none at all. The planet continues, indifferent, and evolution tries again. This is a humbling thought, but it's also strangely liberating. It means we're not outside the pattern, we're part of it. We're subject to the same forces, environmental change, resource limits, extinction dynamics that shaped every lineage before us. Our intelligence doesn't exempt us. Our technology doesn't save us. We are animals on a planet with finite resources, and like all animals, we can fail. The difference is that we know. We can see the pattern. We can measure the extinction rates, model the climate scenarios, understand the consequences of our actions. We have the tools to change course if we choose to. Whether we will is the question that defines our moment in history. And if we don't, if we continue down the current path and trigger the sixth mass extinction in its full catastrophic extent, then we join the synapsids and the dinosaurs, dominant lineages that rose, flourished, and fell. The Earth will remember us as a thin layer of sediment with strange chemistry, a spike in extinctions, an anomalous moment when one species briefly reshaped the world before vanishing into deep time. Millions of years later, whatever intelligence arises next might wonder, as we have wondered, whether they are the first. They might search the rocks, find faint traces, and debate their meaning. They might never know we existed, or they might find just enough evidence to suspect, but never prove, that something intelligent came before. And the cycle, as always, will continue. So we return to where we began, 300 million years ago, to a world unlike any that exists today. Pangaea was real. It formed as continents collided, piece by piece, over tens of millions of years, until nearly all of Earth's land was joined into a single immense supercontinent. It lasted for 160 million years, longer than the reign of the dinosaurs, longer than the age of mammals, longer than we can easily comprehend. It was a harsh world in many ways, with vast interior deserts and extreme climates, but it was also a world of complexity and diversity. Forests grew along its coasts, rivers carved valleys, ecosystems thrived, and it was ruled by synapsids, creatures that were neither reptiles nor mammals but something in between, a lineage that would eventually give rise to all mammals, including us. These were not primitive animals. They were sophisticated, adapted, successful. Some were warm-blooded. Some may have had fur. Their brains were growing larger. Their social structures were becoming more complex. They dominated the land for over 100 million years, a span of time that dwarfs the entire history of human civilization. Then came the Great Dying. 252 million years ago, the Permian Triassic extinction erased 96% of marine species and 70% of terrestrial vertebrates. The causes were multiple: volcanism, climate disruption, ocean anoxia, but the result was singular. The world nearly ended. It took more than 10 million years for life to recover, and when it did, the synapsids were no longer dominant. The age of reptiles had begun. This is the world we've explored, and throughout this exploration, we've asked a simple question: could an intelligent species have arisen on Pangaea, developed a civilization, and then vanished without leaving traces we could detect? The answer, it turns out, depends on what we mean by could. Could it have happened in the sense of being physically possible? Yes. The prerequisites for intelligence were present. Time was abundant, 160 million years, more than enough for evolution to produce complex cognition if the right selection pressures existed. Energy was available. Many synapsids were endothermic, capable of sustaining metabolically expensive brains. Social behavior was emerging. There is evidence of pack hunting, herding, and group living. Brain sizes were increasing, particularly in the synodonts, the most advanced synapsids. The raw materials were there. Did it happen in the sense of being probable or supported by evidence? Almost certainly not. The evidence weighs heavily against it. No geochemical anomalies have been found in Permian strata, no carbon isotope spikes from fossil fuel burning, no synthetic radioisotopes from nuclear technology, no nitrogen or phosphorus concentrations consistent with industrial agriculture. The fossil record shows gradual evolutionary change, not the sudden leaps or ecological disruptions you might expect from an intelligent species reshaping its environment. Synodont brain sizes, while larger than earlier synapsids, were still far smaller than those of early hominins. No tools have been found. No evidence of controlled fire. No structures. The simplest explanation, that synapsids, despite their sophistication, never crossed the threshold into intelligence, is almost certainly correct. Would we find evidence if it had happened? This is the most difficult question, and the answer is probably no. 250 million years is an almost incomprehensible span of time. Plate tectonics has recycled much of the seafloor that existed during the Permian. Erosion has worn down mountains, filled in valleys, buried coastlines under kilometers of sediment. The Permian Triassic extinction obliterated ecosystems and scattered fossils. Any civilization that existed before the extinction would have been swept away, their artifacts ground to dust, their bones fossilized and mistaken for those of animals, their geochemical signatures, if they left any, buried so deep or eroded so thoroughly that we would never recognize them. Even if a pre-industrial civilization arose, one that built with wood and stone, communicated orally, lived along coastlines, and left no metal or synthetic materials, it would be invisible to us. The wood would have rotted, the stone monuments would have weathered away, the oral traditions would have died with their speakers. The coastlines they inhabited are now subducted beneath tectonic plates or submerged under rising seas. We would have no way to detect them. They would be ghosts in the geological record, present in history but absent from evidence. This is what we've learned. Not that a civilization existed on Pangaea, it almost certainly didn't, but that the question itself is valuable. It forces us to confront the vastness of deep time, the limits of what fossils can tell us, the biases embedded in how we search for intelligence. It reminds us that absence of evidence is not always evidence of absence, especially when dealing with timescales measured in hundreds of millions of years. It also teaches humility. We assume we're special, that intelligence is rare, that civilizations like ours are unique in Earth's history. But the truth is, we don't know. We have one example, ourselves, and a fossil record that captures perhaps 1% of all species that have ever lived, preserving snapshots of anatomy but erasing almost everything about behavior, cognition, and culture. We are looking for signs of intelligence through a keyhole and declaring, based on what little we can see, that we are alone. Perhaps we are. Perhaps intelligence is difficult, improbable, a rare alignment of traits that took 4 billion years of evolution to produce and may never occur again. Or perhaps intelligence arises more often than we think, but civilizations are fragile, lasting only thousands or millions of years before collapsing, leaving no durable traces in a planet that erases its history with ruthless efficiency. If the latter is true, then we are not the first. We are simply the latest, and we may not be the last. Millions of years from now, after we are gone, another intelligent species might arise, descendants of rats or crows or octopuses or something we cannot imagine, and they might look at the rocks, find faint chemical anomalies from our time, and wonder, as we have wondered, whether they are alone in history. The cycle continues. Life evolves. Complexity emerges. Extinctions wipe the slate clean. Evolution tries again. This is the pattern, and we are part of it, not separate from it. Our intelligence does not place us outside the natural order. Our technology does not guarantee our survival. We are animals on a finite planet, subject to the same forces that shaped every lineage before us. The question is not whether we will leave traces, we already are, but whether those traces will tell a story of wisdom and adaptation, or of hubris and collapse. Can we accept that we may never know the full truth about Pangaea? That some questions cannot be answered, no matter how much we study, how carefully we search, how sophisticated our methods become? Can we live with uncertainty, with the knowledge that the Earth keeps secrets, and some of those secrets are lost forever? Beneath the Appalachian Mountains, worn down from their ancient height, lie the roots of the central Pangean range. Beneath the Atlantic Ocean, where the mid-Atlantic ridge slowly spreads, lies the ghost of Pangea's rift, the scar where the supercontinent tore itself apart. Beneath the Pacific seafloor, being pulled into subduction zones, are fragments of crust that once bordered Pangea's western coast. Somewhere in those rocks, crushed and melted and mixed with the mantle, are the remains of creatures that walked Pangea's shores, breathed its air, lived and died under its skies. If an intelligent species existed among them, their bones are there too, indistinguishable from the bones of animals. Their tools, if they made any, have been ground to sand and scattered. Their thoughts, their languages, their cultures, their achievements, all are gone, erased by time and geology and extinction. They are as invisible to us as we will someday be to whatever comes after. The Earth does not remember. It recycles, it erodes, it subducts, it forgets. And so the question remains, unanswered and perhaps unanswerable. Beneath the supercontinent, beneath the mountains and oceans and deserts that have come and gone, beneath the layers of sediment and the flows of lava and the bones of a billion creatures, could something intelligent have lived there, looked up at the stars, wondered about its place in the universe, and then vanished, leaving nothing behind but whispers in the rock? We will never know. Perhaps that is the lesson. Not that we are special, but that we are temporary. Not that we are alone, but that we cannot prove we are not. Not that the Earth revolves around us, but that it will continue long after we are gone, carrying our story or forgetting it, with the same indifference it has shown to every lineage that came before. Beneath the continents, the mantle churns. Beneath the oceans, the plates drift. Beneath the sky, life continues its ancient experiments with form and function, trying new combinations, testing new strategies, rising and falling in endless cycles. And somewhere, deep in the rock, compressed and altered and lost, are the traces of Pangaea, a world that was, a time that passed, a story that no one will ever fully read. The Earth sleeps and dreams and wakes to new eras and sleeps again. And in the morning when you wake, the mountains will still be there, worn a little lower. The oceans will still churn, spreading a little wider. The continents will drift infinitesimally toward new configurations. And the Earth, patient and indifferent, will continue its slow work of forgetting everything that came before. Beneath the supercontinent, beneath the time, beneath the question, only silence remains.